All right, guys. Afternoon. Online, can you hear me and see the screen clearly?
Yes, sir.
All right, so we're gonna do some work today, some revision work on at least 3 topics: transformation, quadratics, functions. And the idea is to look back at the main things that we're supposed to know for these topics and do some questions, practice some questions where we're applying those must know things. All right. So on the screen, what I'm gonna do, I'm gonna just take the first part of the session to touch on each of the topics that we're doing. And we're gonna just go back to some of the main things that we're supposed to know for these topics. And then maybe take a short break, and then we'll just go into doing questions. All right. So for the first part of the session, we'll just focus on going back to some of the main things that you're expected to know to do questions. So on the screen, I'm starting with transformation. And this is the most known sheet in transformation that I would have presented to the class. Transformation must know sheet. Things that we need to know in transformation. And basically, it is broken down by type initially. So here in this block, or in this entire row, I'm talking about translation. Remember, translation is a transformation where the object moves without turning. It moves from one location to another. All right. And to describe a transformation, to describe a translation fully, you must always give the name of the transformation. And if you're describing a translation, you really need to say how many units left or right, and how many units up or down. That's how we describe it. And the translation matrix, or a translation, can be represented by this column matrix, where this value is the number of units horizontally, left or right, and the second value is the number of units up or down. When this value is positive, you go to the right, and if it is negative, you go to the left. And then this second value, if it is positive, it is the number of units upwards that you go. And if it is negative, this one, if it is negative, it is the number of units downwards. And then the combination of the horizontal and the vertical will result in the final translation. All right. In terms of calculation, it will move a point by this. So you add the x is added to the a. So a point x, you add the a to it. And the y coordinate at a point, you add the b to it. You add the b to it. So that's calculation wise. So in this example here, I have a translation 3, 4. So that translation 3, 4 will move a point like this to 10, 12, because you're adding 3 to the 7. You're adding 3 to the 7, so the 7 plus 3. And you're adding 4. You're adding 4 to the 8 plus 4. All right. In terms of the actual movement on a graph, a point is going to move. If you have a point here and you're applying this translation to it, it's going to move 3 units to the right, and then it's going to move 4 units upwards. And this point was 8, and this is now A prime. 3 units to the right, 4 units upwards. That's what that translation would do. If you're applying this one, where the two values are now negative, this negative 2 means 2 units to the left, and this negative 5 means 5 units downwards. So it's negative 2, negative 5. And so graphically, a point, if a point is here, I apply this translation to it, it's going to move 2 units to the left and 5 units downwards. That's a negative 5. And so a point here would end up here, and that would be an A prime. Calculation-wise, it's a similar thing. You're applying this translation to this point. You're taking 2 from the 6, subtract 2, that's this minus 2. And you're subtracting 5 from the 3, that's minus 5. That's this 5 you're subtracting from the y value. And so that would be the result of that translation. All right? That's the most simple of the transformations, really. Translation. Image and the object will look exactly alike on graph paper. All right? They will look exactly alike. There's no turning, no change in size, anything like that. Just move from one location to another. All right? Let's talk about the next one, which is enlargement. Well, let me leave enlargement for last. Let's talk about the others first. Let's talk about reflection. I'll talk about reflection in a line. Now, the key about reflection is that the image distance from a mirror line is equal to the object distance from a mirror line. You can also reflect through a point, and that's why we have from a point here. But we are really focusing on reflection in a line. All right? Image distance from the line equal to object distance from the line. So for example, if I have a point here, and I have a mirror line here, then the image of this point is going to be over here, such that this distance to the mirror line is equal to the same distance on the other side of the mirror line. That's a key thing. Image distance equals object distance from the mirror line, and it is on the other side of the mirror line, perpendicular across. All right? To describe a reflection, reflection only has one component. You state the mirror line. And if it's a point, you can state the point, but we're not getting into the point. We're focusing on the lines. So you all have to do to describe a reflection is say it's a reflection and say what the line is. Reflection has one component, which is the mirror line. Say what the line is. That's how you describe a reflection. You cannot just say it's a reflection. You have to say a reflection in which line. You have to state the line when describing a reflection. All right? Then now there are a number of reflection matrices that you are required to know. It's very good to know. 5 of them are here. CSEC will set questions that test your knowledge of these reflection matrices. If you don't know them, screenshot it. Take a screenshot of this. And you need to know these matrices. It helps to know these matrices. Chances I might not use them in the exam, but then chances I might use them in the exam. Because there are questions that will give you a reflection and then they will ask you for the matrix for that reflection. You need to know them. All right? Now, in the class, I thought you meant that to memorize them. But now, I mean, we did this from last year. You're supposed to know them by now. All right? So this is the y-axis reflection. This is the matrix for reflecting in the y-axis, this matrix. This one is for reflecting in the x-axis. Notice the negative one was at the top for the y-axis. And the first negative one there, the negative one is on the other diagonal down here, across from it. All right? That's for the x-axis reflection. Then we have reflection to the origin. We have reflection to the origin. The negative is on both of them. But then we also have reflection. So these are the main ones, you know. These are the main ones. These are the main ones for reflection. Those 4. It's like a broader one for reflecting to a point. All right? Those 4. This is a reflection in line y equals x. In my line y equals x and line sloping up like that, passing 2 points with x and y value the same. So you pass through like 0, 0, pass through like 4, 4, pass through like 10, 10. Pass through points with the x and y value the same. That's the line y equals x. This is the matrix for reflecting in the line y equals x. And one good thing to know about that one is that the x and y values are reversed. So our xy point will simply be reversed to yx when you reflect in the line y equals x. And then this one now is kind of easy to know. So if you know the y equals x, then it's kind of easy to know the y equals minus x. Because all that happens is that these two ones, they become negative ones. All right? And a similar thing happens. So this now, reflecting line y equals minus x. So the line that goes like this, y equals minus x. Passes through the origin 0, 0, yes. It passes through points where the x and the y value are the same value but opposite sign. So for example, pass through negative 2, 2. And the pass through negative 4, 4. And if you continue down this way, it passes to a point like maybe 2, negative 2. That's for reflecting in that line, this matrix. All right, it's good to know those matrices. All right, it's good to know those matrices. And how this one works, more things you know, the better. How this one works is that a point xy, they're going to be reversed to yx, but they're also going to change sign. All right, that's what happens. The reverse, just like the xy, but also change sign. All right, so for example, 3, 2 is going to go to -2, -3 with this reflection. But this one, the values just reverse, switch out. So for this one, a point 2, 3 is going to go to 3, 2, 3, 2. All right, so that is reflection in a line. There's one important thing to remember about reflection in a line, and it is right here. This thing right here. Orientation is reversed when you reflect in a mirror line. It is the only transformation that reverses orientation. What do I mean by orientation? Orientation is basically how the vertices and a shape go around the object in alphabetical order, clockwise or anti-clockwise. So for example, if I draw a triangle like this, and I name the vertices A, B, C this way, then A to B to C is right now anti-clockwise. That's how they turn. If I draw a triangle again like this, and I name the points A, B, C this way now, then A to B to C this time is this way, which is clockwise. The orientation is the opposite. These two orientations, they are opposite. And if I see this triangle and this triangle, is a result of a transformation. And no, it's a reflection in a line because the orientation is reversed. Reflection in a line is the only transformation that reverses orientation. A lot of the times, a reflection and a rotation can look alike. To make the distinction, you can check the orientation. If the orientation is reversed, you know you have a reflection. And the mirror line is always halfway between corresponding points. So for these two, which would be the result of a reflection, the mirror line will be right down the middle here, such that the distance of B to the mirror line is B prime from the mirror line. C to the mirror line is C prime to the mirror line. And A is all the way out here, whichever one is the object and whichever one is the image. Because image distance equals object distance. The orientation is reversed. This thing is very, very important for deciphering between a rotation and a reflection that might be a little bit confusing to you. Check the orientation. If the orientation is reversed, then you know you have a reflection in a line, because a reflection in a line is the only transformation that reverses orientation. Rotation does not reverse orientation. Orientation stays the same after a rotation. All right? So let's remember that. We're going to apply all of these to a couple questions. I'm just touching back some of the main points. You can always watch back the video. And, you know, it is said, you have to know stuff to do the exam time. You have to know stuff. All right? Then we come to rotation. Rotation. Rotation is when an object turns about a center. So rotation has three components. And if you're describing a rotation, you have to state those three things. You have to state the direction, whether it's clockwise or anti-clockwise. You have to state the angle of the rotation in degrees, 90 degrees, 180 degrees are the two angles that they mostly give you for rotation. All right? And you also have to state the center of the rotation, where is the center of the rotation. Sometimes the rotation, the center of the rotation is the origin. Most times the origin, but as the CSEC is setting a lot of questions recently, where they are giving you rotation where the center is not the origin. And you have to be able to find those centers. I can just say it now. The center of the rotation is on the point of intersection of lines joining corresponding points. If you look at the January 2023 exam paper, that transformation question, You see where we have to construct the center of the rotation. All right? And you can look at my channel and you can see the video for that solution if you want. All right? So we don't set it more often. We have to construct to find it, but they did it recently. Most times you can actually see where the center of rotation is. Most times it's the origin. I'll do a couple of examples and show it. And then now there are some rotation matrices. These are the two main ones. Oh, one more thing about rotation direction. One more thing about rotation direction. Anti-clockwise rotation is positive rotation. Clockwise rotation is negative rotation. So instead of saying, for example, 90 degrees clockwise, a question can say negative 90 degrees rotation. I have to know that negative 90 degrees means clockwise. Anti-clockwise rotation is positive, clockwise rotation is negative. I see CSEC question like that already. I see that on multiple charts. I remember it clearly. It's like they give a rotation and they give a diagram, right? For a rotation. So it's like, let's give you an example quick. So it's like there was an object maybe here, and this was A and this was B. And then it turned and it is now like this. A is now up here and B is now down here. So you know the rotation is down this way, but this B has rotated down to here. Right? And the center of rotation may be somewhere in there. So let's say, for example, right? Wherever it is. Let's put it this way then. Let's say that was A and now it is rotated down to here. That's been rotated down to here. So this was B and this is now B prime. And I asked you to describe that transformation. It is clearly a rotation about the point A. It's 90 degrees. I know it's 90 degrees because this was horizontally first and it is now vertical. The angle between horizontal and vertical is 90 degrees. And the direction of this rotation would clearly say it is this way, clockwise. And then the answers that they gave for you to choose from, they gave positive 90 degrees, they gave negative 90 degrees, gave 180 degrees, and they gave maybe 360 degrees. You know, it's one of these two. That's clearly 90 degrees. Or you know which one it is, positive or negative. You have to remember that clockwise rotation is negative. So the answer would have to be this one because it's clockwise. So for myself, why is it that it's clockwise is the one that is negative? That's how it is. I tell people all the time, what you can remember is that if you think of the X and Y axis, this is the positive quadrant. I have to rotate the X-axis up this way to reach into the positive quadrant. That's why anti-clockwise rotation is positive. You get me? So from 0, you go up into the positive quadrant this way. So anti-clockwise rotation is positive rotation. So if you see this question, you have to remember that. You set this question. All right? So if you set on multiple choice, you can set on paper 2 as well. All right, good. This is revision now. I'm telling you, I like to speak sometimes some of the things that they don't say often. All right, but let's talk about the matrices now. You're also expected to know these matrices, guys, the rotation matrices. And these are rotation matrices about the origin. A rotation about the origin, all of them. So when the center of the rotation is the origin, these are the matrices that can be used for the calculation. These are the matrices that represent those transformations. We're going to see how we use the matrices later. Now, a couple of examples. You multiply the matrix by the point, by the object point to get the image point. And that's why transformation comes in the matrices part of the syllabus in section 2. But this is the clockwise 90-degree rotation matrix, 90 degrees. This one, this matrix right here. And this one is the anti-clockwise one. Now, how I remember it, I do a thing like this. I put the arrow up like this for anti-clockwise. I remind me that the negative one is at the top over there. For the anti-clockwise 90 degrees rotation about the origin. And then if the negative one is at the top for the anticlockwise, then it's at the bottom down here on the other diagonal. They're on the same diagonal, you know, the one and the negative one, they're on the same diagonal. Just that for the anticlockwise one, the negative one is at the top. I remember where the negative ones are. So I say if I rotate this way, the negative one is going to be up here. That's all I remember where the negative one is for the anticlockwise rotation. But I remember in this little rotation arrow there. These are the two main ones for rotation we need to know. The clockwise 90 and the anticlockwise 90. Then this one now is a 180 degrees rotation about the origin. And if you notice, it is the same as the reflection to the origin. These two matrices are the same. Look at them. They are the same, these two. So a 180 degrees rotation about the origin is the same as reflecting through the origin. We can extend that to any point. A 180 degrees rotation about any point is the same as reflecting through the point. So a question might ask you, for example, to do a 180 degrees rotation about this point, for example. So let's say I have a triangle here. And I ask me to do a 180 degrees rotation about this point. You might be trying to rotate it. It is easier to just reflect through the point. Let me draw a triangle like this instead. It might just be easier to just reflect through the point. Treat the point like a mirror. Right? So instead of trying to rotate this 180 degrees, reflect through the point. So this point, the distance from here to the mirror point is this. It's the same distance on the other side. So this point coming to here. Then this one come to the mirror line, to the mirror point, you go the same distance on the other side. Oh, let me take this call. They might be here. Hello? The outside. All right, cool. Somebody coming. Yeah. All right, sorry about that, students. Right. So I'm saying we can reflect this point through the mirror point as well until come over to here, to there. So this distance and this distance is the same. And then you're doing this one as well. So this point to the mirror point is here, same distance on the other side to here. And then that will be your image triangle. So instead of trying to rotate, we just reflect through a point. So remember, 180 degrees rotation to a point, the same as reflecting through the point. All right, so hopefully we might come up on an example we have to apply that. So these two are the same. All right, so that is your rotation. All right, now we have a special kind of transformation that we call a glide reflection. Glide reflection is a combination of a reflection in a line and a translation that is parallel to the mirror line. Key thing is that the translation is parallel to the mirror line. That's what this one is. A glide reflection. A reflection in a line and a translation that is parallel to the mirror line. All right. Hopefully I can come up on an example like that. Then these things are good to know. They help you with questions when we have compound transformation, two transformations. All right. First one is that two reflections over lines that intersect is equivalent to a rotation. The point of intersection of the two lines is the center of the rotation, and the angle of the rotation is twice the angle between the lines. I'll give you a quick example now. Quick example with this one. Quick example right here. So let's say I have y-axis and I have the line y equals x. Y-axis and y equals x. And I have a point here. And this is the origin where they meet. That is the origin O, where the y-axis and the line y equals x meet. And I have this point P that I'm going to reflect in the y-axis first and then the line y equals x. Note that these two lines are 45 degrees apart. So if I reflect in these two lines which intersect, this rule or this thing that you must know is saying we are supposed to get a rotation. So the two reflections over these two lines is supposed to result in one rotation. And the angle of the rotation is twice the angle between the two lines. So the angle of rotation is supposed to be 90 degrees. And you literally can see it. If I reflect in this line first, it's coming to here. This distance and this distance is the same. Then if we're reflecting this line now, it's coming to here, about here. So this was my original point. I did the two reflections. It is now at this point. It's called a P double prime. To go from this to this is a single rotation. So if I put a line here as a center, put a line across here, you can literally see that this angle between these two purple lines is 90 degrees. So from this to this is a 90-degree rotation and 90 degrees rotation. Because we did two reflections over lines that intersect and the lines are 45 degrees apart. So sometimes question CSEC will test another of that. They will give you these two reflections. They will give you a y-axis reflection, then a y equals x reflection. Then I might ask you the last part of a question. What single transformation takes P to P double prime? You need to know that it is a clockwise 90 degrees rotation about the point, about the origin. Why? Because the two mirror lines, the two blue mirror lines are 45 degrees apart, so the rotation angle is 90 degrees. And the point of intersection of those two intersecting mirror lines is the origin. So the origin is the center of the rotation. It makes sense to just know that you don't have to be figuring it out if you know it. More things you know, the better. If two lines are 90 degrees apart, they're going to end up with a 180-degree rotation. So for example, if you're reflecting the y-axis and then the x-axis, let me show you. And see if you like to set these questions, reflecting the y-axis and then the x-axis. So you have the same point over here again. Reflecting the y-axis first, it comes to here. They're reflecting the x-axis, it comes down to here. Those two reflections, this is P and this is the final position, P double prime. Is it equivalent to a rotation through this point of 180 degrees? See here? This to this, this to this, it is a 180 degrees rotation. That 180 degrees rotation about the origin. Why is that? Why is it 180 degrees rotation? 180 degrees rotation. Because the angle between the y-axis and the x-axis is 90 degrees. So the rotation angle is twice that. So CSEC, you can give you a question where they say, okay, reflecting the y-axis and then reflecting the x-axis and then ask you, what single transformation will map P to P double prime? It's good to know that that is going to be a rotation about the origin, because the y-axis and the x-axis intersect at the origin, and the angle of the rotation is twice the angle between those two lines. Angle between the y-axis and the x-axis is 90 degrees. The rotation angle is going to be 2 times that. See there? Must know. These things make question easy. You don't have to be figuring out stuff in the exam. The less things you have to figure out in an exam is the better. All right? Then we have this one here. Two reflections over parallel lines is equivalent to a translation. And the distance between the distance of the translation is twice the distance between the mirror lines. That's when we have parallel lines. Give you a quick example, quick and fast on this. Quick and fast. All right? We're crashing this thing. So let's say I have a triangle like this. Make the triangle turn up so then. Let's say I have a triangle like this. And I have two mirror lines, two parallel mirror lines. One here and one here. That's two mirror lines. I'm going to reflect this in this triangle first. All right? So this point is going to come to here. Same distance going to come to about here. This point is further away. So it's going to go about over to here. Same distance across. These two distances are the same. It's going to come to about here. And this point is going to come right under it over here. Over here. So initially, this is my initial image after the first reflection. Then if I reflect this now in the second mirror line, and this point is going to come to about here. This point is going to come to about here. This point is going to go a further distance away, right across to about here. So my image after the second reflection is going to be this. If you look at these two, the original one and the final one, they are the same. And so from this one to this one is a translation. Because we do two reflections over parallel mirror lines. So we end up with a translation. The size of that translation or the distance of this translation, maybe from this point to this point, for example, from here to here, that distance, which is the length of the translation, is twice the distance between the two mirror lines. So the distance between two mirror lines is 5 units. The distance between two mirror lines is 5. Then the distance, I'll put it here, so the distance between the two mirror lines is 5 units. Then the distance between the distance of the translation is 10 units. Twice the distance. The translation distance is twice. I can say the translation direction is perpendicular to the two mirror lines. Translation direction is perpendicular to the two mirror lines. These are things that help if you know them. You don't know what's coming on the exam paper. More things you know, the better. All right. So this is all on the must know sheet. I need to touch on the enlargement. All right. Still up here. When I come back down to the compound transformation, let's touch on the enlargement a bit. Enlargement. So the enlargement transformation is one now where the size changes. Sometimes we call it size transformation. Whether the thing gets larger or smaller, it's still called an enlargement. It is the scale factor that decides if it gets larger or smaller. So for example, if the scale factor is 2, the image is going to be twice the size of the object. But additionally, you have to remember that scale factor also affects distance from the center of the enlargement. Enlargement as a center. So if the scale factor is 2, the image is going to be twice the size of the object, twice as large, but also it's going to be twice the distance from the center. If the scale factor is half, then the image is going to be half the size of the object. So the size is going to be half. But the distance from the center of the enlargement also is going to be cut in half. So remember now, scale factor can also be positive, it can also be negative. When the scale factor is negative, the image is now going to be inverted on the opposite side of the center. I would say it's inverted. You know it's inverted when the image and the object now are pointing in opposite direction. All right, so let me give you a little image quick and faster. So let's say I have a triangle like this. This is a triangle like that, and this is A, B, C. And I do a transformation on it, and my image is like this. And now my C is down here, my B is here, my A is over here. It's an enlargement, you know, because it gets bigger. But this is going to have a negative scale factor. Now, if this was 1 unit, if this side was 1 unit, and this side, corresponding side is now 2 units, then I know the scale factor has a value of 2, because it has grown by a size of 2. If this was 1 unit, and this is now 3 units, then the scale factor has a value of 3. But the scale factor negative, or one way negative, because the image and the object, they are pointing in opposite direction. What do I mean by that? If you look at the B to C, the B to C is pointing up. But on the image, the B to C now is pointing down. So it's an enlargement, gets larger by a value of 3 times, but then it's a negative 3 because it has been inverted and it's now pointing in the opposite direction. And any one of the sides you look at, you're gonna see it. If you look at A to B is this way on the object. A to B is this way on the image. They are pointing in opposite direction. Right? So that is it, guys. You have to look out for that. And then now the image distance equal the object distance. Now, if you want to find this, if you want to find the center of the root of the enlargement, you just join the corresponding point like A to B, B to B prime, and say C to C prime. Let's draw it like this, C to C prime. Mean that this will be the center of the enlargement. And the scale factor is 3. It means that this distance has been tripled to that distance. Just have to go on the opposite side of the center of the enlargement. That's when a scale factor is -3, for example. All right? If the scale factor was a positive 3, then the image and the object would basically be pointing in the same direction. So you maybe have something like this. If I draw about the same little triangle, ABC like this, and then the image is now like this, just bigger. And this is ABC. This is ABC. Okay, I'll put the prime on the image one. That's an enlargement. That's a positive scale factor. Because on the image, the object and the image pointing in the same direction. So for example, BC pointing up on the object, BC still pointing up on the image. So you know that a positive scale factor. And the side of the scale factor, again, if this side was, for example, 1 unit, and this corresponding side is now 3 units, you know the scale factor is now 3. And how you find the center of this enlargement? Same way again. Join the corresponding points and see where they intersect. So if I join C and C prime, like this, and I join A and A prime, like this, and extend it back, where those lines meet is the center of the enlargement. So enlargement has 2 components. There's a scale factor, that has a center. So if you're describing an enlargement, you have to give those 2. I have a calculation here for enlargement, but it's common sense almost. But generally speaking, is that image length divided by a corresponding object length, give it the scale factor. Image length divided by a corresponding object length. But most time you can see how much it has grown by. If this enlargement goes the opposite way, if this enlargement was the opposite way, this one, let's say this was the object, the big one was the object, and the small one was the image. So put the prime on this one now. Prime, prime, prime. So the transformation is this way, from big to small. The scale factor will be 1/3. If this side was 3 and this side is now 1, the scale factor is 1/3. Because you have reduced the size by 1/3. So the scale factor would be 1/3. And a positive 1/3 again. Right? So that is it, guys, in a nutshell. And let's talk about some other features. Let's talk about some other features of this thing. That's good to know as well. This is the matrix for enlargement about the origin. K00K. K is the scale factor. All right? And remember, this is when this matrix is only valid when the center of the enlargement is the origin. And the K is the scale factor. And how it works, it's very easy. You multiply the coordinates of a point by the scale factor. So if a point was 2, 4, and the scale factor is 3, then this point is going to go to 6, 12. I multiply the values by 3. That's how it works. That's how enlargement about origin works. So it's an easy transformation when the center is the origin, the enlargement. All right. Now this one is also very important to know, guys. Area of images equals K squared area of object. So we do enlargement area. Let's write it like this. Area of image is equal to scale factor squared times the area of the object. This is very good to know. When they bring area into play, they start to ask you about area. For length, for distance, the length of the image is just K alone times the length of the object. That's for distance. But this is for area. When it's area, you have to square the scale factor. Area of image is K squared times area of the object. So sometimes I might ask what is the ratio of the area of the image to the area of the object. You divide the area of the object over here and you end up with this. Area of image over area of object is equal to K squared. Becomes equal to K squared equal K squared, the scale factor squared. CSEC asks questions about that from time to time. All right? These are some things that we must know. And then here now is basically just some examples of what I've been saying with the scale factor, positive or negative. So the scale factor is 2. What are some of the things that happen? The image is twice as large and also twice the distance from the center. And they are on the same side of the center. And they are pointing in the same direction because of the positive scale factor. Pointing in the same direction. And this one, if scale factor is negative, it's going to be twice as large because of the 2, twice the distance from the center because of the 2, but because of the negative now, it's going to be inverted, means pointing in the opposite direction, and they're going to end up on opposite side of the center. All right? And if the scale factor was like a half, 0.5, then the image is going to be half the size. It gets smaller by half. It's also going to be half the distance from the center. And the image and the object will be pointing in the same direction and they'll be on the same side of the center because of the positive scale factor. And then if it's a negative scale factor, half, again, the half will make it half the size, half the distance from the center. But the negative now inverts it, have the image and the object pointing in opposite direction, and they are now on opposite side of the center. These are the most known things for transformation, basically. All right, then we come down to here now. So compound transformation down here. So we're talking about the 2x2 transformations first, the 2x2 transformation matrices. And I apply this in the matrices all the time. When you have two transformations, M followed by L, two transformations, M and L, and the two of them are 2x2 transformations. Both of them are 2x2 transformations. This means that we're not talking about translation. Translation is not involved in this rule that I'm going to talk about now. Why? Because translation is not a 2x2 transformation. It's a 2x1. Look back at it. Translation is a 2x1 matrix represented. All the others are represented by 2x2. See there, the enlargement is a 2x2. The reflections are all 2x2s. And the rotations are 2x2s. So for the ones that are 2x2s, this rule applies. A transformation followed by another transformation. If you want to get a single transformation which represents these two consecutive transformations, which are 2x2 transformation, we're not talking about the translation. Translation not involved. Then the single transformation which represents the M followed by L is obtained by multiplying L times M. You multiply the second one by the first one. The second one by the first one. So for example, if two transformations are P followed by Q, make the pen small, right? So for example, two transformations, P and Q. P followed, not writing. Let's go again. P followed by Q. Those are two transformations. Is equivalent to Q times P. So you do the calculation Q times P, it will do the transformation for you in one step. How it works, we have a diagram here, right? See a diagram here, so we're using the M and the L and the M again. So here, we're doing M followed by L, two transformations. So the M is the first transformation, might be a reflection, or a rotation, or an enlargement, followed by another 2x2 transformation, L. Again, can be a reflection, an enlargement, or a rotation. Translation not involved in this, for this rule. Then the single transformation is obtained by multiplying the second transformation by the first one. Not this, remember, not this. The second transformation multiplied by the first one. If you see LM, it means M followed by L. If they give you a compound transformation and they say this is a compound transformation, LM, it means M followed by L. See here, LM means M followed by L. So they can give you M followed by L, or they can just give you LM. You have to know that LM means M followed by L. All right? So look at it this way. If I'm doing LM on a point P, the M is closer to the P. So that the M is going to work on the P first. Think of it that way, similar to functions, composite functions. So the M is going to work on the P first. And the M is going to move the P to P prime. That's what the M does. The M move the P to P prime. And then the L takes effect now. The L jumps in now and does its thing. The L takes it now to the final destination. That's doing it in two steps. So see it on the diagram here now. If I'm doing M followed by P, which is the same as LM. That's how it's represented. I take the P and I put the M on it first. It takes it to P prime. See, it takes it to P prime. The M takes the P to P prime. Then the L applies to P prime and takes it to the final destination, P double prime. That's if you want to do it in 2 steps using both transformations. But you can use a single transformation that you get when you multiply them. When you multiply the L times the M, and you get a single transformation. That single transformation, LM, you can just apply that single transformation to the P, and to take it all the way over to the P double prime. CSEC expects you to know that. All right? I'm going to see if we can do a couple of questions with that one as well. All right? This is an example over here. We have these 2 transformations, L and M. Then M followed by L is LM. So you see, I multiply the second one in front of the first one. See, I multiply the second one in front of the first one to get the final transformation matrix. All right? So that is it. So all of this is on the mouse now. I can screenshot it and show you note. And then we have inverse transformation. So inverse transformation works similar to how inverse function works. It reverses a map, it reverses a transformation. And inverse transformation, all of them are common sense. Translation. You just do the opposite of what the original translation did. So a translation move your 2 units to the right and 2 units up. If our translation move your 2 units to the right, let's take it up this way. 2 units to the right, a translation. 2 units to the right and 3 units up. Then the inverse is going to move your 2 units to the left, mean -2, and 3 units down, mean -3. Because you're going backwards, you're going the opposite direction. Inverse of a translation, you're going the opposite way. You're trying to go back where you came from. Right? That's inverse of a translation. That one is common sense. Then inverse of a reflection in a line is to just reflect back in the same line. Because if you have a mirror and a mirror maps an object to an image, and you want the image to go back to the object, you have to reflect the image now in the same mirror line. So the inverse of a reflection in a line is the reflection back in the same line. Inverse of a rotation about a point, you should just do back the same rotation in the opposite direction. So 90 degrees clockwise rotation about a point, and when the inverse, there's an anti-clockwise 90 degrees rotation about the same point. Just reverse the direction. Same angle, same center. Then the inverse of an enlargement, no, common sense again. If you double the size of something in the originally, you have a half but the size. So the inverse of an enlargement of scale factor 2 is an enlargement of scale factor half, about the same center. So they are common sense. It's not rocket science. So we don't want to spend too much time on this. And then now, if a matrix M does a transformation, then the matrix M to the -1 will do the inverse of that transformation. We'll reverse the mapping. And how do we get M to the -1? The same way how we do it in matrices. 1 over the determinant of the M multiplied by the adjoint of the M. And we did matrices last week. So any transformation matrix that does something to a point, the inverse of that matrix will do the opposite. We'll reverse it. We'll reverse it. All right? So that is it in a nutshell, guys, for transformation. This is the same thing. If M maps P onto P prime, then the inverse of M, that's M to the -1, is going to take the P prime and take it back to P. See it in a diagram form here. If you have a point P and the matrix M takes it over to P prime, then the inverse matrix is going to take the P prime back to P. Inverse matrix. All right? So the inverse of a transformation matrix, the inverse of a transformation of a matrix, of a transformation matrix, you use the inverse matrix to do it, to reverse the transformation. And since you ask a question like that, what? They give you a matrix and say, okay, this matrix map a point A from point A to B. What so for example, the matrix 2, 3, -1, 6. Map a point A to B. And they say, what transformation will map B back to A? The inverse of this, they want. The inverse will map it back, will carry it back, just calculate the inverse of this matrix. Same here, 1 over the determinant multiplied by the adjoint. The inverse of the matrix will reverse the mapping. That's transformation in a nutshell, guys. Transformation in a nutshell. Just need to do questions. Yeah? Huh? You don't have to do it separately. You can do it in one go. So first, wait a minute, you mean like, no, they like when you put, they like when you calculate the determinant inside the matrix. So if you have 1 over 2, you want to divide each of the values by the 2. You understand me? And get the actual matrix. All right? We do sometimes do, if you're going to use that matrix and you're going to apply the fraction, you can leave the fraction for last. Like we're solving the question. That's what we normally do, right? But if you ask for the inverse matrix itself, carrying the 2, don't leave the fraction outside. I'm not saying them penalize if you leave it, but just give them the matrix. Carry the fraction, the half inside or whatever it is. All right, good question. All right, guys, that's transformation. Most know one can screenshot this and screenshot this. You must know things in transformation. Open you can see it. The thing that you must see and apply. All right. I send me a WhatsApp and I send it to you. All right, that's transformation. What do we do? Do questions in transformation or do we touch other topics first? What do you prefer do? Last week we just touch all the topic them first. Take a break and then we just do questions. We don't want it. We want us to go to the other topics topic. Let's go to the other topics. All right. So the next topic to touch on is either function or the quadratics. Let me see. Let me touch on the quadratics a little bit, right? Let's touch on the quadratics and remind ourselves of the quadratics. All right, so I have a must know sheet right here, so. And there's quadratics in it. There's a quadratics section in it that I want to use. Revise the quadratics. Revising the quadratics as we learned it in this class. All right? And I'm doing it as we learned it in this class. All right, because, seminar we do. Yeah, that's I'm recording. You can go back or listen to it again. Everything I'm doing here now, we have done already. You know, everything I'm saying here, I've said it before. Just that you weren't here from the beginning. You're gonna have to do some additional work. Yeah. So yeah, that is it. So we have to just go. So we are where we're at. So you just have to just catch up, catch it, fine. This one is quadratics now. This one is quadratics when we look at. So I don't look at transformation, quick and fast. The main things that touch on transformation that you need to know. We're touching quadratics now. And in particular, we're talking about the completing the square and the quadratic curve, maximum, minimum, and these things. Right? Those are the person who said they wanted quadratics. That's what they mainly wanted, I'm sure. All right? All right. So for a quadratic function is represented like this. You have a square term, an x term, and a constant in it, right? For it to be a quadratic, the square term has to be in it. So you can have a quadratic with no b term in it, with no x term, mean that the b is 0. So it can be that there's no b term in it, so the b is 0. And you can also have one where there's no c term, c is 0. But you can have a quadratic if there's no square term. So it is the square term that makes it a quadratic. That's the first thing, right? Then we have the letters A, B, and C. What we said about quadratics is that the A is always given to the coefficient of the x squared. The number in front of the x squared is given letter A. How about they set it out? So for example, if they give you a quadratic like this one, then the A is 2, the B is -4. You have to see the sign in front. So the A is 2, the B is -4, not just 4, and the constant term, the C is 3. The A, B, and C kind of important for the method that we're going to be using to complete the square. We need to know those values. And A, B, and C also important when you're solving the quadratic equation to find roots, right? If using the quadratic formula. All right? If they give you now an equation now, and the equation instead was like 4, with the different numbers. So they give you a function, and function was f of x equals 5 minus 7x minus minus 4x squared. So even though the square term appears third in this expression, this is still the a value. Coefficient of x squared is a equal -4. And the coefficient of the x, this one will be the b value. That will be the b equal to -7. And even though the 5 appears first, it is a constant term, it is still given letter c. C will be equal to 5. All right? So that's how we choose the A, the B, and the C. Not based on the position of them in the expression, but based on what their coefficients are. So the coefficient of the x squared is given letter A, coefficient of the x is given the letter B, and the constant term is given the letter C. No matter where they put it in the expression or they arrange the expression. All right, that's the first thing. Then now, CSEC will often ask you to do what we call completing the square, to complete the square. And they might not use the term complete the square. They might simply ask you to write the expression in this format to look like that, where we have what we call a perfect square in there. That's what I've just circled, what we call a perfect square. Is perfect square. When it is like that, we are able to identify the vertex point or the turning point. So we call it a turning point form of the quadratic function. This is called the standard form, and this is called the vertex form or the turning point form. Because this kind of helps you to know where the turning point is. All right? Now, the problem with this, though, CSEC tend to set the question like that most of the time. But sometimes they'll give you, for example, a into x minus 8 squared plus a. Instead of a plus, I put a minus. Sometimes I might give a into x plus b squared plus c. Sometimes I give a into x plus b squared plus q. Different ways of setting. So because the CSEC might change up how they arrange this thing from time to time, I say, you know what, let us stick to one standard way to do it. And we're going to use a way where the expressions tells us, where the expressions tell us what we have. So instead of writing it like this, we choose to write it like this: a into x minus xt squared plus yt. Where t means turning point. T means turning point because a quadratic function has a turning point. And so xt is the x value at the turning point when you use this method, and yt is the y value at the turning point. So when you use this method, you are finding the coordinates of the turning point right away. And this is the formula for xt using the a, the b, the a and the b as I just explained it. Xt equals negative b over 2a. You just have to know it. And yt is this formula: 4ac minus b squared divided by 4a. You can also find xt and yt by using the xt value back in the function. When you find the xt value, you put it back in the function to calculate the yt. You can calculate yt that way as well. By putting whatever value you get for xt after this calculation, put it as the x value in the function here, work it out, and that is the yt value. But xt and yt are coordinates at the same point. Xt, yt are coordinates at the same point. Yt is the y value on the function when the x value is xt, where t simply means turning point. All right? T means turning point. Oh, look here. This is the first topic I did in September. So, but it's supposed to master this. It's the first topic that we did in this program, September. First class in September. That's what we did. All right? So that's how we calculate xt and yt. And we can then put them in this. See here, so put them in that. All right? Then there are some other spin-offs that we get from x and y. So this example, these values, this is a calculation for xt. See there? Look. The b is -4, so it's minus b. See there, minus a -4. right here, minus -4. That's what I have up here. So divided by 2a, and the a is 2. So the a there, the a equals 2. So 2 times a becomes 2 times 2. That's what I have right here. So I get a 1. And now that we get a 1, let me show you right away. We could have calculated the yt by taking the 1 and put it back in the function here and there for the x. So we could have gotten yt by doing 2 times the xt is 1. You put 1 here, so you put 2 times 1 squared minus 4 times 1 plus 3. If you work this out, you're going to get 2 minus 4 plus 3. You're going to get 1. Because that's a -2 plus 3 is 1. See, when you use a formula method, you get a yt value of 1 just the same. So normally, when my xt come out to be a whole number, I don't bother use this formula method. I just put that whole number value back in the function and work it out like I just did. Get it easier than to use a formula method with all those fractions. Get me? But when it's not a fraction, when the xt comes out to be a fraction value, like maybe if I get xt equal -3/2, then I might not bother with the -3/2 back in the function. Just use the formula to find yt, this formula, to find yt as I did right here. Let's look at it. So again, the a is equal to 2, the b is equal to -4, the c is equal to 3. See there? A, B, C. And I'm putting those values in this form. So see there, it becomes 4 times the A value, which is 2, times the C value, which is 3. That's 4AC. Minus. The B is -4. See, they are squaring -4. They divide it by 4A. See, they divide by 4 times A. The A value is 2. And then work out itself. You can literally now just put this in a calculator if you want. And work it out here. I think to remember about this is that this minus is not squaring. It stays back a minus. It stays a minus. You're not squaring. You're only squaring this. So the square is not on that minus. So the -4 becomes a 16. From the positive 16. And it works out itself. All right? And that's how we get the values to write the vertex form, complete the square. And then once you find the xt, you know, see here, once you find the xt and the yt, so the xt is 1, the yt is also 1. So this one is coming here, and this one is going there. And so we end up with this. And the a is coming here, the a equals 2 is coming here. And so that's how we end up with this. So it becomes x2 into x minus 1 squared plus 1. That's how we get that. All right? So that's the first part, writing it in the vertex form. Then now, there's some spin-off upstairs I forgot. So the A tells you the shape of the quadratic function. The quadratic function will either smile or frown. When the A is greater than 0, meaning positive. When the A is positive, this means positive. When the A is a positive value, the graph is going to have a smile shape. A smile shape is like this. So it comes down to a minimum, and again, then it goes back up. That's why I say that a minimum value, a minimum point, when the A is positive. So when the A is positive, the graph will have a smile shape, and it will have a minimum point and a minimum value at that minimum point. What are the minimum values and the points at that point? So this example over here, you can see it. When the A is positive, the function has a minimum value. What is the minimum value? The minimum value is the y value at that point, the yt value. And it occurs at the same point where the x is the xt value, when x equals xt. So in this example that we did up here, the minimum value is the 1, And it occurs when x equals the xt value, which is 1. So the minimum point is 1, 1. The minimum point is the point 1, 1. Xt, yt. All right? Xt, yt. Hope we'll get some questions to do. Then now, when the a is negative, the graph is going to have a frown shape. So it's going to go over like that. It's going to have what we call a maximum point with a maximum value. Maximum value is the y value, the highest y value on the graph. Same yt value. All right? So in this example, this is the function after we complete the square. All right? So I didn't bother work though, but for this example, see, if you notice the a is negative 2, we're going to end up with this vertex form. And in that case, we know our maximum value, f of x is the maximum value of yt. And that yt value now is just negative 1 out here, which occurs when x equals xt. So in this example now, the xt value is right here, and the yt value is this negative 1. And so the maximum value is the yt value, which occurs when x equals to 1. So the maximum point is 1, negative 1, because that's xt, yt. That becomes your maximum point. That becomes a maximum point. All right? Also remember that a quadratic function has a line of symmetry, or what we call an axis of symmetry. Because the parabolic graph, the quadratic graph has a parabolic shape that is symmetrical about this line. So when it smiles, as a line down here that passes through the turning point. Passes through the turning point. And the equation of that line is the line is x equals whatever the xt value is. That's the equation of the axis of symmetry. That line is called the axis of symmetry or the line of symmetry. If it was a frown shape, same thing. The frown shape quadratic graph. Then again, you have a line of symmetry, pass through that maximum point, and the maximum coordinates points at that point. Coordinates at that point is xt, yt. Same here, so xt, yt. Just at this one minimum, and this one up here is maximum. And the equation of this axis of symmetry is still x equals whatever the xt value is. So if this point was, for example, 2, 4, then this line will be x equals 2. If the point was 2, 4, for example, x equals whatever the xt value is. This line is called the line of symmetry or the axis of symmetry. Axis of symmetry. Some people spell symmetry with 1M or 2M, depending on whether it's English or American. Axis of symmetry, or sometimes the line of symmetry. Divides the graph into two halves. So what that means that the y values on either side of this line will always be the same. Same distance across from it. The y values here and the y value here is the same. So the y values are symmetrical about this line of symmetry. The y values that you get. The y value over here and the y value over here is the same y value for those two different x values. You see at this point, the y value at that point is the only point that has that y value. Same thing here, so. It's the only point that has that y value. Every other point on a quadratic graph, the y value is repeated on either side of the line of symmetry. So at the vertex point, at the turning point, it's the only point that has that particular y value. Either it's a minimum y value or maximum y value. All the other y values are repeated on either side or on the opposite side of the line of symmetry. So this point over here, so might be, for example, say 3, 3, 2. Over here, so might be minus 4, 2. See, the y value is the same. Y value is the same. Let's give you an example on either side of that line of symmetry. So the y values are symmetrical, and sometimes we can use that information to complete the table when they give you. You don't have to be calculating everything. You can look for the symmetry in the values. I'm going to see that, I'm sure, in some examples. All right. Anything else? So we did this down here. I think in a nutshell, that's quadratics. That's quadratics in a nutshell, in terms of what I want to say. What about maximum, minimum, and thing? We're going to sketch a graph. There's also roots. Roots, remember the points of the graph intersect x-axis. So if you have a quadratic function, and you have the x-axis, you have a y-axis here, and these 2 points are called the roots. They're called the roots. And you get those points where you solve the quadratic equation. Ax squared plus bx plus c equals 0. But on the y-axis, on the x-axis, the y value is 0. So you solve this to find the roots. Solve it to find the roots. I can solve it by factorizing. I can solve it with the quadratic formula. When you solve it, the x values that I get are the x values here and here. They are normally two roots. Two roots. And solve this using the quadratic formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a. So in this formula, you get one root with the plus, you get the other root with the minus. So you get two roots. The roots x equals that. So when you equation it in this form, this quadratic equation, I call it quadratic equation, you solve it to find the roots. So every time you want to find the roots, you can basically solve the quadratic equation. Put the function equals 0 and solve it. Why is that? Because at these 2 points, the y value is 0. The y value equals 0 on the x-axis. Y value equals 0 on the x-axis. So you can put the function equals 0 and solve it to find the root because the y value is 0. That's all the other thing I'm going to talk. And there's also the y-axis intercept. Can I mention that as well? So for example, in this one, yes, CSEC like to ask you to show the y-axis intercept. Undo. They like to ask you to show the y-axis intercept. So the constant here always tells you the y-axis intercept. So if the function y-axis, x-axis, I know that gives graph as a smile shape, and the turning point on this one is 1, 1. So somewhere up here, 1, 1 is somewhere up here, 1, 1. So, and it has a y-axis intercept of 3. So if I were to sketch this one now, it would maybe look like this. It turns at 1, 1. And it crosses the y-axis at this constant value 3. So this point is always 0c. 0c, which in this case is 0, 3. The y-axis intercept, we cross the y-axis. It's always a c value, 0c. That's 3 on the y-axis, where this example would cross the y-axis. Right? So those are the things. See, they like to ask about the turning point and the y-axis intercept and the axis of symmetry. They like to ask those three things. And sometimes they ask about the roots as well. Those are the critical things. And then the shape. But the shape, the A positive, it will smile. If the A negative, it will frown. Those are the main things. All right. Next thing we'll encounter this is in question. Let's talk about functions quickly. And I'm going to start with the definition of what a function is. I'm using this as an example just for that point. What makes a relation a function? All right? So a function is a relation in which each element in the domain map onto one and only one element in the range. All right, the codomain. What that means? It means that it is the domain. Yeah, man, I cannot bring it from me. It is the domain that decides if you have a function or not. You good? Yeah, man. It is the domain that decides if your relations are function or not. You have to look to your domain. You don't really care too much about what's happening over the codomain. When you do math at a higher level, yeah, it becomes a little bit more important because you can have functions, you can have different types of functions, but they don't deal with that at CSEC. At CSEC, you're only concerned about a one-to-one function or a many-to-one function, but there are some other types of things that can happen. depending on what is happening in the codomain. And there's a difference between codomain and the range. But CSEC not really getting into that too, right? I can maybe mention it, but not too much. So rule that says each element in the domain must map. Each really means every single element in the domain must map. And when it map, it must map only one time. So in simple terms, you cannot have any free element in the domain that is not mapping. And when the element in the domain map, it must map only one time. In other words, you must only see one arrow coming off the element in the domain for that relation to be a function. So this is an actual past perfect question, asking which one of these is a function. I want to look at, which one I say? B. B is the only function. Good. Because in this first example here, this first one, there are two values in the domain that spoils it. This one don't have any mapping at all. So that alone would make it not a function. And then this one has two arrows coming off it. It's mapping twice. So that's a one-to-many. One-to-many relations are not functions. So those two that have circled cause it not to be a function. The second one, each of them have one arrow coming off them. So this one is good. That's a function. Because each of these have only one arrow coming off them, mapping over into the codomain. So that one is good as a function. This one is not a function. This one down here is not a function. The three elements spoil this one. This one spoil it because it don't map. This one spoil it because it map more than one time. And this one spoil it because it don't map. So this one is bad as a function, not a function at all. And then this last one, again, this one spoil it. Because that one maps two times. So each element must map one time alone. Hey. Can go outside. What's wrong with you? All right. So this one good as a function. So those three good as functions. Those, sorry. This one no good. This is no good. This is the only good one. This is the only good one. This is not good. And these are the two reasons. I ask, so why this one not good? These are the two things I have to tell you. You ask, so why this one not good? I have to tell them the three of them. If you ask, so why this one not good as a function? This one make it not good. Because each element must only map one time. All right? Then now, we also have the graphical aspect of what can make something a function or not. And this is an example says, which one of these is a linear function? See, linear. Now, firstly, you need it to be a function. We also need it to be linear. So linear means line. So know that is one of these two. But these are not linear. These are curves, right? But a relation is a function graphically if it passes what we call a vertical line test. I remember I told you about the vertical line test, the V-line test, B-line test, B-line test. And then you also have the H-line test. So the V-line is telling it's a function or not. This one tells you function or not. Function or not a function. The V-line test. That's how we always do it first. Do the V-line test first. And then the horizontal line test tells you type of function. It tells you if it's a one-to-one or many-to-one. Let's put that. It tells you if it's a one-to-one or many-to-one. A relation can be either a one-to-one function. A function can either be one-to-one or many-to-one. So the vertical line test tells you when you have a graph, the vertical line is what you would use to decide if the graph is one of a function or not. So you do the vertical line test first, and then you do the horizontal line test second. Because you have to know if it's a function first before you can say what type of function it is. You can't go saying what type of function it is before knowing if it is a function or not. Because, for example, if a graph is shaped, shaped like this, and you go do a horizontal line test on it first. And the horizontal line will intersect at one point. So because the horizontal line intersect that at one point, you might believe that that is a one-to-one function. Because when you do the horizontal line test, 1 point of intersection means a one-to-one function. More than 1 point of intersection means a many-to-one function. If you do the horizontal line test on this graph first, you might say it's a function, a one-to-one function, because it's a 1 point of intersection. But this actually is not a function. It's not a function, because if you do the vertical line test on it first, do that first, it intersects at 2 points. And when you do the vertical line test on a graph, the vertical line must only intersect at 1 point for it to be a function. Because what this means is that you have one x value mapping to two different y values. So this is a one x value mapping to two different values of y. That's a one-to-many relation. And so it is not a function, not a function. Not a function. So when the vertical line crosses the graph at two different points, then you don't have a function. That's what we need to do. When we're testing function on and type of function on a graph, do the vertical line test first. The vertical line must only intersect the graph at 1 point for it to be a function. If it intersected more than once, it's not a function, because if it intersects more than once, it means that it's a one-to-many relation, which is not a function. All right? So if you look at these examples over here, some people might have say, which one of these can it be? Because they say, okay, let's say they eliminate these two because they are not lines, for the simple word of the lines. They say, okay, none of these. One of these two. We're going to know which one it is. This fails a vertical line test. A function cannot have any vertical section on it. Because a vertical line and a vertical section will intersect more than once. Because if I put a vertical line on this vertical graph, like so, to test it at my vertical line test, and I go like so. See, they intersect it and intersect this so, intersect it all over. So it fails. Because a vertical line on a vertical line intersects at an infinite number of points. So this cannot be a function, not a function. This is not a function. It's not a function, so it's not the answer. Because it's not a function. It's a line, but it's not a function. Because it fails the vertical line test. But after that, this one good. Look at this. Any vertical line you draw will intersect this at only 1 point. You see? Your vertical line is a 1 point, 1 point, 1 point. So it is a function. And then now, if you do the horizontal line test, any horizontal line you draw can only intersect this at 1 point. So it's a one-to-one function. It's a function first. What kind of function? A one-to-one function. And it's linear. So this must be the answer. A linear function. A linear one-to-one function. All right, let's talk about the other two on the page, since we have them. Vertical line test first on this one. Any vertical line I draw on this one will intersect at 1 point. So it is a function. Yes, it is a function. Because any vertical line I draw will intersect at 1 point. Do the vertical line test first. So we know it's a function. Okay. After we know it's a function, what kind of function is it? Is it one-to-one or many-to-one? You can do the horizontal line test. Any horizontal line I draw will intersect this graph at only 1 point. So it is a one-to-one function. That's what we have right now, a one-to-one function. But it is a curve, it's not linear. That's why it is not the answer for this question. Because it's not linear, it's a curve. Get me? But it is a one-to-one function. Then if you look over onto this one now, which has a quadratic shape. This one's a quadratic shape. Any vertical line you draw can only intersect this graph at 1 point only. See there? So it is a function. Yes, it is a function. It is a function. And I want to know what kind of function it is now. One-to-one or many-to-one. When we do my horizontal line test. Horizontal line intersect at 2 points. And so it's a many-to-one function. Why is it many-to-one? Because look, two different x values. See there, one x value over here, so like maybe it's 4, and another x value over here, so like maybe -4, giving you the same y value of maybe 5. That's a many-to-one, right? So like -4 map into 5, and 4 also map into 5. So it's a function. It's a many-to-one function. When the horizontal line graph, when the horizontal line and a function graph, that's a function graph because past vertical line test intersect more than 1 point, then it's a many-to-one function. Right? It's a many-to-one function. So this one is a many-to-one function. Many-to-one function. All right, so start out with the graph, start out with the mapping diagram. Sometimes this thing helps, right? Not just about the calculations alone and the f of g and so on. But we can start about some of those now quickly, right? And then we take a short break, but stretch them legs, and we'll come back and we hit a couple questions, right? We're going now for about almost hour and a half already. Wow. We started late, so maybe we got over it. But let us touch on a couple other things about functions, right? So we do the mapping diagram, we did the one-to-one, horizontal line test, vertical line test, inverse function. So the inverse function, it reverses what a function does. I want to see how you calculate that. A lot of teachers teach it x and y, interchange the x and y, and you reverse the calculation. So like, for example, if you had f equals 3x plus 7 as a function, it can be f of x. Some teachers say y equals 3x plus 7, and then inverse it and put x equals 3y plus 7. Then transpose the y the function, and then have the inverse, right? But Mr. Shaw does this. It's basically the same thing. I have to do the same operation anyway. So instead of calling x and y, I just leave it as f, and I say, okay, inverse it. F becomes x 3 times, the x becomes f to the -1 plus 7. And I'm trying to make that the subject. And I make that the subject, that's my inverse of this function up here. So when I make this the subject, 3 over the 7 first, I will get x minus 7. Then this 3 I will divide under here. X minus 7 over 3, that is f to the -1. And that's my inverse function, right, of this function. All right? And remember, the inverse function reverses the mapping. So again, if a function f takes a value like maybe 3 and carry it over to 10, then f to the -1 will take the 10 and carry it back to the 3. Right? That's what it works. So you can say f of 3 equals 10. F to the -1 of 10 equals 3. Right? Something like that. And one thing to note, only a one-to-one function can have an inverse. Only a one-to-one function can have an inverse. All right, CSEC don't really test that too much at CSEC level, but only a one-to-one function can have an inverse. You have to be able to reverse the mapping. Right? So if you have a one-to-one, you can reverse a one-to-one and get a one-to-one. If you have a many-to-one, can I tell you quick? If you have a many-to-one, I try to reverse many-to-one, you're gonna get back a one-to-many. What do we say about one-to-many? One-to-many is not a function. One-to-many are not functions. So you can't reverse a many-to-one and back into a one-to-many. You're getting back something that is not a function. When you find the inverse of a function, you get back a function. Right? So only a one-to-one can have a function, can have an inverse. All right. So this is good. This is good as well. So we can set up a thing where we say, okay, if f of x equals any number, whatever that number is, then the x right here, so is equal to f to the -1 of that number. Something similar that we just did here. Like a reverse mapping, because like we are saying, x is mapped onto n by the f. And so the inverse is mapping the n. The x now becomes equal to the inverse. The inverse is mapping the n back to the x, the inverse, f to the minus 1. So f to the minus 1 of the n is now equal to the x. All right, so this is good to solve some equations sometimes. All right, we're going to see the use of that later on. We also have composite functions. So like, for example, if you have two functions, f of x equals 3x plus 7, I have g of x equals square root of x plus 4. You want to form f of g of x. Remember, this really means the g function into the function. That means g first. So you put in the g into the f. When you put the g into the f, you take all of the g and bring it and put it into the f wherever the x is right here. Simple as that. So that will become 3 times all of the g, which is the square root of x plus 4. You want to put in a bracket, fine, plus by the 7. We go in the other way and do it g of f of x. Then I write them back again. Write them back again. So again, if I'm doing the other way now, I have f of x equals 3x plus 7. And I have g of x equals the square root of x plus 4. I have these two now. And I'm now going to do g of f. Then I can do the f into the g. Meaning I take all of the f and put it into the g where the x is right here. So this is going to simply become the square root where the x is. I'm putting all of the f there, which is 3x plus 7 plus 4. And then you simplify it. That's what form the composite function. Another thing, if we're doing of a value, if we're doing of a value, like composite of a value, like if we're doing g of f of 3. G of f of 3 means that we can do g of, can work out the f of 3 first. Can work out f of 3 first and see what f of 3 is. So if the f a while ago was what? The f of x is 3x minus 7, for example. Then this will become g of f of 3 means I want to put 3 in the f function right here. It will become 3 times 3 minus 7. And this will work out to 2. So now we'll be doing g of 2. And the g function is the square root of say 14 plus x. They'll put the 2 in the g function right here now. And then this will simply become equal to square root of 14 plus 2, which is square root of 16, which should be 4. Something like that, right? Another thing to remember is that f squared, for example, if it's a composite function like this, f squared of x. F squared of x means f of x means f into itself, right? So if f of x was 3x minus 2, f of x is 3x minus 2, then this means f on itself, or f into f. So I can take all of this f and put it into this other f. And so this will simply work out to be 3, where the x, I'm putting all of the f there again, 3x minus 2, and I'm subtracting back this 2 out here, minus 2. And then simplify that. So remember, if it's the f squared, don't go square in the function. F squared means f of. All right? One other important thing we can know about function is this. F to the minus 1 of f of any number will equal about the same number. That's enough calculation. So f to the minus 1 of f of 7 automatically is going to be equal to 7. Why? Because like you apply a function upon 7 and then you reverse it back. It's like you drive forward and then you drive backwards. You're back at the same place. Because remember, function and inverse are like reverse of what one does. So it's like a drive and reverse in a car. So the drive carry you forward, the reverse carry you back. So if you apply the drive and you apply the reverse same time, then you're coming back to where you were. So f to the minus 1 of a f of a number, give about the same number. CSEC test that from time to time. That don't need no calculation. Waste of time to calculate on this. And the reverse it and put f of f to the minus 1 of 14, same thing, still equal 14. Yeah. Because these are inverse of each other. Two of them are inverse of each other, same way. This is the inverse of that, and this is the inverse of that. They are inverse of each other. So when you composite inverse functions, you get about the same value. Get me? Simple as that. Boom, bang, boom, bang, boom, bang, boom, bang. Anything else? Oh, undefined. Remember when a function is undefined? I'll talk about rational function. Like, for example, if f of x equals 7x plus 4 over say 3x plus 6. This function cannot work if the denominator becomes 0. Any value of x that will make the denominator become 0 cannot be in the domain. Remember, if it is in the domain and it's going to be a function, it has to map onto a value. Any value of x that will make this denominator 0 cannot work out to be anything. So, for example, when the 3x plus 6 is equal to 0, the x is going to be equal to negative 2. So it means that negative 2 cannot be in the domain. Of f of x can't be in the domain. Why? Because negative 2 going to make it become 0. If you try to work out f of negative 2, you're going to get 7 times negative 2 plus 4 over 3 times negative 2 plus 6. It's going to become 0. So you're going to get negative 10 over 0. This can't work out. So it means that the negative 2 would not have any value to map onto. When it can't work out, we say it is undefined. It is undefined. Undefined. That's a term that they like to use. So the value of negative 2 will make the function undefined. So negative 2 cannot be a value in the domain because it will not have a value to map onto. And you cannot have a function when there's a value in the domain that is not mapping onto something. You get me? So negative 2 will make this function undefined. So for this to be a function, the x cannot be negative 2. X cannot be negative 2. X can be any value except negative 2. And sometimes CSEC will ask you that question. What value of x will make this function undefined? It's the value of x that cannot be in the domain. And all you have to do is put the denominator equals 0 and work out what the value of x will make the denominator equals 0. As I did right here. So all you have to do. Undefined. All right. Then we have inverse of a composite function. The last thing I'll touch on. Inverse of a composite function. I think I might deliberately do a question because I don't set this very often. I think since we started the mock exam, we don't do one of those questions. I think maybe there was one on the paper that we did today. And I deliberately figure out those papers that we did today for the simple reason that some of the questions and those papers don't come very often. Some of the questions. So we're doing a lot of bearings. Don't say in a composite function, inverse of composite function. So all inverse of composite function works is this. Like f of g all to the minus 1. That's inverse of f of g. Remember, it is equal to g to the minus 1 of f to the minus 1. Look at it carefully. All right, CSEC will test your knowledge of this in multiple ways. All right, but this is it is centered on this. Now, look at it carefully. F of g here has been reversed to g of f out there, and you inverse there. What does this mean? What does this one mean? This one means that we'll find a composite function first, f of g, and then we inverse it. That's what that one means. This one means to find the f of g first, and then you inverse the f of g. This one means that you find the g to the minus 1, you find the f to the minus 1 separately, and then to work this out, you put the f to the minus 1 into the g to the minus 1. When you work this out and you work this out, they're going to be the same. They're going to be the same when you work them separately. What CSEC does sometimes in some questions, right? They give you two functions. They ask you to find a one there. They ask you to find a one there. Then them say, hence, find this fg r to the minus 1. They will usually say hence or otherwise still. They say find that. They usually say hence or otherwise. So otherwise, you could find this by itself by working on the f of g and then inversing it. But when them say hence find this, it means that they wanted to use these two to find this. How do you use these two to find this? You have to know that this thing is actually now equal to g to the minus 1 of the f to the minus 1. So you see the g to the minus 1 you find and the f to the minus 1 you find. You put the f to the minus 1 into the g to the minus 1. You put the f to the minus 1 into the g to the minus 1. And whatever this works out to know is the answer for this. So it's very good to know inverse of a composite function. Right? Inverse of a composite function. All right. I think that is it in terms of touching. We're going to take a 10 minutes break. So now, all right, let's start back at 6 o'clock with question. All right. I'm going to take a quick run through. We're going to start back at 6 o'clock with question. Yes, yeah, give you on the time to. Yeah, I'm going to give you a time to put the box. Maybe. must have. Oh, CT, that's true. Yeah. And, which pretty much skills a couple. 85 more minutes. Let's give it 5 more minutes. All right, call them for me. Tell them ready again. Call them outside for me. Tell them to come. Call them for me, please. Answer them. I'm gonna start on it. All right. This is some questions. And it's true, a couple questions here. CXC basically set the question at the same standard every year. One about the same way. Recent times they've been given tables by the complete. And you can actually see the symmetry in the values of the tables. I would maybe the one or two of those. So let's start with uh, do this again. All right. 2015 to 50. All right, I'm gonna do a couple questions from 2015. Start. All right, so 2015 question 6B, I think it's a transformation question. We're just picking questions randomly to practice from. All right. This one is actually a quadratics. Let me start with this one. Okay. All right, let's do this one first. The quadratics.
Serious screen is black.
My screen is blank. Thanks. Thanks for that. Good now?
Yes, sir.
Thanks for that. If anything happens, let me know, yeah? I'll be back here and see what you see. Anything around, let me know. All right. So we're looking at this 2015 June exam paper. This quadratics question number 4. They tend to set question like this in section 2 notes. Part question 2. All right. So this question gives us this table. And it's for this function. It's a quadratic function. As you can see. So it's square term there. And they give us some values, and we're expected to fill out these two. Now, once these x values are the same interval, then the y values will be symmetrical about a line of symmetry. Y values will be symmetrical, right? About an axis of symmetry. So I'm picking up these two negative values. Remember, the y values repeat, you know. And to the right of this value, because it's like the axis of symmetry is somewhere in the middle there, and the y values are the same going outwards from that line of symmetry as we did on the graph. So same way the values are symmetrical on the graph, same way that it's symmetrical in the table. All right, so oftentimes you don't have to calculate all the values. So I can tell you right now, to the right of this value is that empty cell, and to the left of this value is that empty cell. So whatever value is here, the same value in both of them. Because if you notice, to the right now of this cell is 5, and to the left of this cell is 5. Remember, the values are symmetrical outwards from a line of symmetry. Now, this symmetry, you can know the symmetry by taking the average of these x values. Why not can take the average of these x values? Because the symmetry, because these two x values given the same y value, symmetry is halfway between these two. The line of symmetry is halfway between those two. I mean, when I show it to the graph, I said the x value here and x value here is the same. The line of symmetry is right on the this distance and this distance is the same. Get me? So because these two y values are the same, and the result from these two x values, the symmetry is halfway between these two x values. Halfway between 0 and 2 is 1. Halfway between 0 and 2 is 1. It means that this is your vertex. This is a symmetry. Your axis of symmetry means that your axis of symmetry is right here. That is the vertex. That's a turning point right here. Right? Because everything now is going to be equal to the left and to the right from that point. So this is actually a vertex. Sometimes they give you the point, sometimes you have to figure out the point. In this example, they give you the point. So this is your turning point. This becomes your minimum point. I don't have to calculate it. This becomes your vertex. Right there. That vertex is your xt, yt. Right now. Xt, yt. So xt is this, yt is that. That is your turning point. That's your vertex. It's a minimum. Or it's a minimum because the square term is positive. So it's a minimum turning point. It's a minimum turning point. And I can use that to write my vertex form. I don't have to calculate. Because I know my xt and my yt value. You get me? Then now I have to calculate one of these two. Anyone I calculate, I know the other one. They are the same value. I will calculate both of them to show you that they are the same. But I know already that they're going to be the same because of the symmetric nature of these values. So let's start working out this one. Here, you're going to plug this tree in the function. Right? You don't give a lot of space to work on here, but we can work it out right here. So this value is when you plug 3 in the function. So the y value is going to be 3 squared. So x squared becomes 3 squared minus 2 times 3, because this x value is 3, and then minus 3 again. That becomes 9 minus 6 minus 3. That becomes 0. So this is 0. That value there is 0. If this value is 0, then automatically this value is 0 as well. I want to prove that this value is 0 by calculating it. Or you get, or you get that value for calculate. You put -1 in the function for x. So it would have worked out to be -1 squared minus 2 times -1 minus 3. This -1 squared become a +1. Put it down here, so. This -2 times -1 becomes a +2. And then subtracting this 3. See, it equals 0. I did not have to calculate that one because I know that the values are symmetrical. You have to do the mathematics the easy way. All right? That is it. So those are the values. I've completed the table with those values. Next thing I want us to do is put these points on the graph. See, on the graph, plot the points, 1 unit to 2 centimeters to 1 unit on the x-axis and 1 centimeter to 1 unit on the y-axis. All right, so we're using 2 centimeters to 1 unit on the x-axis, 1 centimeter to 1 unit on the y-axis. That's what they tell us to do. If you look at the scale, you're going from -2 to 4, and it's 2 centimeters to 1. All right, and then you have to look, we're going to put a y value. This graph has to go down to -4 and goes up to 5. So you have to be careful about where you put the axis, the x and y axis. So you can accommodate all those values. Get me? But we're going from -2 to 4. So let's look at the graph that they gave us. So I would venture to put the axis somewhere in the middle to begin and then kind of check it if it would work. So let's say we'll put the x-axis here. I want to shape it up a little bit. And let's say we'll put the y-axis. And we need more on the right of the y-axis. So I see. Go over to 4 and you're going to go back to -2. So you get a little bit more on the right. So if you need a little bit more on the right, we could decide to put our y-axis maybe here. I need to see the word on a square again. All right, so I'm going to make this be the y-axis. I'll make this be the x-axis as I have it here. I kind of leave him on. See if you can straighten it a little bit. Can we straighten it? Even down this end. I can only extend it. Can rotate it a little bit. All right, let me draw it over. It's not coming out so friendly. Yeah. All right, let's just work with it. Let's just work with it right here. All right, and then it's 2 centimeters to 1. So this should be 1, that will be 2, that will be 3, that will be 4. That will be -1 and -2. So it's 1, 2, 3, 4, -1, -2. Then the y-axis is 1 centimeter to 1. So this is 1, this is 2, 3, this is 4, 5, this is 6. We're going on to -4. So -1, -2. -3, -4. So we have a lot of space. That only came down to -4. All right, I'm going to put in the points. So the points that we have, I'm going to write them out here. -2, 5, -1, 0, 0, -3, 1, 4, and I know that that's my vertex. 2, -3, 3, 0. The last one is 4, 5. All right, let's copy these down. So then in front of us, let's copy them down here. I put them right here. And plot in those points, guys. All right. So -2, 5. -2, 5. -2 up to 5 is right here. -2, 5 is right here. Then -1, 0 is on the x-axis. -1, 0 is on the x-axis right here. Then 0, -3. 0, -3 is right here. Then 1, 1, 4. 1, -4. 1, 4, which is actually 1, -4. Right? 1, -4. See that -4. 1, -4 is right here. That's a turning point, you know. That's a vertex. Some questions don't give it a vertex and you have to work it out. All right. Next point is 2, -3. 2, -3 is right here. Then you have 3, 0 is right here. And then you have 4, 5. 4, 5 is up here. So see these values are across from each other. These y values across from each other. And the axis of symmetry would be this vertical line to the turning point right here. So you can say that those those dots are equidistant from that red line. That's the axis of symmetry. Right? And all we need to do now is draw the smooth curve through those points to draw the graph. Let's see what we can do. Let's see if we can do it. So I'm just gonna go like so. See the device we pick it up from. That's a sketch of it. I'm gonna undo it and try again. Device can pick it up from stretch this down and see. Stretch this up a little bit. Trying to see if I can get a perfect fit. Trying to see. Not working out. Let me go back for the sketch that I had. I'll just leave them with that. That's the sketch, all right? Draw it to the freehand best way you can. And that is it. All right, and that's a vertex. That's a minimum point. If you ask anything now, you can answer. It's what they ask us for now. He said, no, complete the following sentences using the graph. Information from the graph. See here now? The values of x for which this is equal to 0. We're talking about the roots. Remember, when you put the function equal 0 and solve it, you're finding the roots. That gives you the roots. And the roots are the values of x to the graph that the x-axis. I want to get from the graph. Right? And it's also where the y value is 0. So that means these 2 points are talking about it. So it's where x equals -1 and x equals 3. So it's also in the table. X equals -1 and 3. Correspond to these 2 points. These are the roots. Roots. X equals -1, x equals 3. Those are the roots. So see here, x equals -1, -1, and 3. See the values of x. The values of x are -1 and 3. Those are the roots. Next one. The minimum value of the function is the lowest y value. See here, the lowest y value on the graph is the minimum value of the function. The lowest value that this function works out to be. The y value at this point, the lowest y value on the graph is right here, -4. -4, the lowest y value on the graph. Right here, -4. Minimum value function is -4. It's a y value at the turning point. The y value at the turning point. It's a yt value, the y value at the turning point. It's -4. -4. Next one. The equation of the line of symmetry, the axis of symmetry is x equals whatever the xt value is. X equals 1. The x value at the turning point is 1 right there. Axis of symmetry is that vertical line that divides the graph. See here? I'm going to put it on in purple. It's a vertical line passing through this point that divides the graph half and half, equidistance from it. So it will be the vertical line through 1 up here, so. That line, x equals 1. This vertical line I'm talking about. Pass through the vertex and pass through 1 is x equals 1. That is the equation of it. X equals 1. Is the axis of symmetry, the line of symmetry. X equals 1. Divides the graph half and half, equidistance. See there, x equals the x bar at the turning point. That is it. Question done. Now, if they wanted you to complete the square from this, suppose they tell us to complete the square, write this in the form a into x plus h squared plus k. I could just simply use a into x minus xt squared plus yt. I would use this. And I know that my x value at the turning point is 1, my y value at the turning point is 4. I don't have to calculate none. My a is the coefficient of the x squared. It do have the number in front, so it is 1. So the A equals 1. So then this would be y equal, the A is 1, the A is 1, bracket x minus the x by the turning point is 1 as well, squared, and the yt value is 4, so it's plus 4. So I could have completed the square from this one because I know the xt and I know the yt value. I don't have to calculate them again. Just use them. That is it. If I ask for the coordinate of the minimum point is the same point, xt, yt, which is 1, negative 4. Same point down here. It's minimum point. That is it. And the minimum value is negative 4. Lowest y value in the graph, the minimum value. X do have the maximum or minimum value. It is a y value. Remember, the function gives y values. The lowest y value it gives is negative 4. That's why I said that's the minimum value of the function. It repeat y values, and it gives you same y value at different point, except at the vertex point, where it is lowest. All right, that is that. Are you good? All right. You good? All right, let's go. So as we walk up on the question, we'll just do it, you know. So we're looking for functions. Number 6b, I think, is a function that transformation on this paper. All right, here's a transformation. Now look here, that see this diagram, you know what kind of transformation it is. You know it's an enlargement. An enlargement is this way. I know it's this way because if you look, this is P and that is P prime. So the thing gets larger. So the scale factor is a value greater than 1. It's not a fraction value, like 2 or 3 or something like that. Then also I know that the scale factor is negative. By just looking at it, I know that scale factor is negative. Why? Because the image and the object pointing in opposite direction. It is inverted. So for example, RP is pointing down this way on the object, but RP is pointing up on the image. So they are pointing in opposite direction. So the image is inverted. And the center point is between them. So I know that is a negative scale factor. And what is the value of that scale factor? Just need to say what multiple one side grew by. So for example, this length was 2 units. That's grown to 4 units. A multiplier of 2. So the scale factor has a value of 2, but is actually negative 2. That's a k value is negative 2. Size of the scale factor is 2, but the scale factor is actually negative 2. Because the thing grew by 2. What also grew by 2? The distance from the center also grew by 2. So the center here. So this distance to R was 1 unit. The distance to the image is now 2 units, but it's on the other side, in the opposite direction. So the scale factor affects distance on the object itself. It also affects distance from the center. Sometimes that is very important. That sometimes knowing that the scale factor affects distance from the center is important. It helps you to describe a transformation sometimes. So you can know what kind of transformation you have for the components of an enlargement transformation. All right. So you are looking at the diagram, you already know the scale factor is negative 2. And to confirm that this is the center, we can join corresponding points. So for example, join P to P prime, like here, the pass through C, and then join R and R prime. So where the lines join corresponding points meet is there, that is the center of the line. All right. So you already know what you need to know. So you can describe this right off the bat. Let's read what it says. Diagram below shows triangle PQR and its image P prime, Q prime, R prime after an enlargement center C. So they're giving away everything. They're telling you everything. They tell you an enlargement and they tell you the center. So they're helping you. They give you 2/3 of the information already. 2 out of 3 they tell you. The whole thing I'm tell you the scale factor. They tell you enlargement, and then tell you the center. So they're helping you. You're getting a lot of help from CSEC in this question. Some questions are not going to help you. You have to figure out everything yourself. They would just tell you a transformation, I must describe it. So you have to tell him everything yourself. It says, use information from the diagram to complete the statement. The size of the scale factor is what? The size of the scale factor is 2. You know, so what is the scale factor? So what is the size? Size of something can't negative. Size of a man is not negative. Length of something is not negative. So once them say what is the size of something, don't put a negative on it. The size is referring to the magnitude of it, not the sign of it, not the positive or negative. The whole body get it. The size of the scale factor is 2. Then it says, yes, you know, the scale factor is negative because what? Because the image is inverted on the opposite side of the center. I can tell them that, and pointing in the opposite direction. Tell them all of that. It's 1 mark for it, number 1, the 1 mark. So tell them everything, but you know why the scale factor is negative. The image is inverted, turn upside down, turn over, inverted on the opposite side of the center. See there? It's on the opposite side of the center and pointing in the opposite direction. Tell them that. So you're going to say the image is inverted. Look what I've written, not inversed, inverted. Invert means turn over, turn upside down. Inverted on the opposite side. When the scale factor positive, the image and the object is remain on the same side of the center. When the scale factor negative, they end up on the opposite side of the center. So the image is inverted on the opposite, looking for words like this, opposite. The opposite side of the center and pointing in the opposite direction. Give them this and them must give you 1 mark. Must. I tell them everything. Tell them say the opposite side of a center, it's inverted and pointing in the opposite direction. Must get a 1 mark. So use up the full line that they give you. That's it. Anything else? The length of PQ is square root of 13 units. Therefore, the length of P prime Q prime is scale factor times it. Scale factor times it. Scale factor times it. Remember, when it comes to length of an image is equal to K times the length of an object. So this is about length. And because it's length, you don't put a negative on it. It's talking about length. Length of something is not negative. So length of PQ is root 13. So length of P prime Q prime is K times 13, but you don't put a negative on the K. So it becomes 2 times square root of 30. Remember, the K is negative 2. But because you're talking about distance, you don't put a negative on it. So the length of PQ, the length can negative, just 2 times square root of 30. But the scale factor applying at a value of 2. The size of 2.
Sir, you can, excuse me, sir, you can go back over that, please.
Go back over which part? Which part of it you want to go back over? From where? From where?
Sir, you reach at the part for the P hold on, go back down, sir.
Down
Go
here,
back
sir?
down, sir. Yeah, right, yes, sir. With the P prime and Q prime.
All right. So this is a P prime and P prime, Q prime is a length corresponding to this. So if we look at the actual object there, they're telling you that this length is the square root of 13. Then this length will be 2 times it twice, because everything is being multiplied by 2. It has to be 2 times the square root of 13. Because everything is being multiplied by 2. Look, this side was 2, It has grown to 4. This side was 1, 2, 3. This side was 3. It has grown to 6. So this side is root 13, must grow to 2 times root 13. You understand that now? Because everything is being multiplied by 2. That's a scale factor of value of 2. Everything is being doubled. Even the distance from the center has been doubled. Look, even this distance is doubled. Look, this distance was 1 unit. That's doubled to 2 units. Look at this distance down to this point. Whatever that distance was, it has doubled up this way. The distance from the center is also doubled. Everything is doubled. Because the scale factor in this enlargement has a size of 2. So everything will be doubled. So if this side is the square root of 13, that side becomes 2 times the square root of 13. Understand that now?
Yes, sir.
All right, good. That is it. All right, so that's how we get the 2 times square root of 13. So we know that everything is being doubled. All right, the corresponding distances are being doubled. Then down here now, they come to talk about area. So the area of PQR is what? So we have to calculate it. So we can calculate it because it's a right angle triangle. And on the right angle triangle, we can just half the product of 2 sides. So this 2 perpendicular sides. So this side is 2 units. This side is 3 units. So the area of PQR is simply half base times height, which is half 2 times 3, which becomes 3 units squared. So that says 3. So the area of that triangle is 3 units squared, don't you, so 3 units squared. So I'll put calculation here, so, and say it's half 2 times 3 equals 3. Also get 3 right here. Fine. Other that, that's the area of the object right now. PQR is the object. This question was testing of our knowledge of that thing I spoke about earlier, which is area of image is k squared times area of object. They're testing your knowledge of that relationship right now. The area of the object right now is 3. And the k has a value of 2. So I can tell you before I calculate anything that the area of the image is going to be negative 2 squared or just 2 squared times 3. So the area of the image is going to be 12. Because 2 squared is 4. 4 3 is 12 units squared. You know that already from this relationship. So the area of the big triangle is going to be this, 12 units squared. I don't see the question, but I know that's what it's going to be because of this relationship. When it comes to area, that's a relationship. When it comes to length, this is the relationship. Sorry. When it comes to length and distance, this is the relationship. Length on the image is k times the length on the object. Our distance on the image is k times the distance on the object. When it comes to area on the image is k squared times the area on the object. That's a relationship when it comes to area. All right, let's see what I'm asked us now. See, you know, the area of P prime, Q prime, R prime, that's the area of the image I'm asking about now. Area of the image they're asking about. Is something times what? See, the testing knowledge of this, you know. Something times the area of PQR, which is the area of the object. This is the area of the object. This is the area of the image. What times? K times. K times. K squared times. K squared times. So what am I write? K squared times. Okay, I'm actually putting the value. Negative 2 squared. You can even put the value of 4 times. See that? Because the K squared is going to come 4 times. So I guess if you put this, they give you your marks. If you put this, they give you your marks. If you put this, they give you your marks. Any one of them, they put them off get your marks. Because you would have already declared that the K is 2, negative 2. Up here, so you have it here so as well. You get me? So if you put, you just need to call it K. Just need to make sure that you call it K. Right? But I guess they may be looking for any one of these. They give you your marks. All of them right. Right? So you can put an equal in between here. So. And I say, which is 1 squared 12. So the area of the image is 4 times the area of the object. Now, they couldn't tell you now, because remember, you had to tell them that this was 3. That's why they really can't tell you. Because you had to work this out. So they couldn't tell you that this is 3. But we know it is 3. And that's why we know that this final answer is going to be 12, because it's 4 times 3. So 4 times 3 is 4 times 3 is 4 times this is 3 is 12 right there. So 12 units squared. So this question was squarely testing our knowledge of this guy right here. So more things you know, the better. Question get easy when you know stuff. More things you know, the better. All right, what good at that? All right. Let's look at number 8B. 8B, I think, is the functions on this paper. So, and to go on a paper, we'll just do all the questions on the topic that we're doing. We're not going to have scotch and back and forth, right? Just exhaust all the questions on this paper for what we're doing today. I know that you want to see some simultaneous equation, don't you? Why? Simultaneous equation are breeze, but I do 2 of them first. I say them do it, right? All right. This one gives us functions, right? The line one and the quadratic one. Yeah. You have a question? Last week. That's what we did last week. We did bearings last week in the marathon. So look back at that video, you'll see. All right, so they give us these 2 functions now. And they ask us for g of 5. G of 5 means they're going to put 5 in the g function right there with x's and work it out. That's what g of 5 means. Don't go put it in this one, guys. Because this is f. G of 5 means you have to go in the g function. A lot of people make that mistake, you know. Gotta put this one first. That's for g of 5. They put the 5 in this one and get it wrong. It's the second one you have to put it into, because the second one is the g. It's the g there. You put it in this one. Don't go put the 5 in the wrong one for me, please. So this becomes equal to 5 squared, where the x I'm putting 5 there. Minus 1 divided by 3. 5 squared is 25. 25 minus 1 is 24. It becomes 24 over 3. 24 over 3 is 8. That is the answer, 8. Nice and easy. X1. Write an expression for f to the minus 1. The one f to the minus 1. The one in terms of x. So the one the inverse of this function. So we're going to start by saying f equals 3x plus 2. Some teacher would have called it y equals 3x plus 2. No problem. I call it the same name as the function. Instead of call it y, I call it f. The math for the inverse of this one, I call it g. Just give it by the same name. No problem. All right? And if you call it y, I call it f, we have to do the exact same thing. I'm going to inverse this function now. I'm going to inverse it. When you inverse it, the f which represents range on this function becomes domain on the inverse. Domain on the inverse function is x equals 3 times. This x which is domain on this function becomes range on the inverse function. Range on the inverse function is with f to the minus 1. And they add back this 2. So this was the function up here. This is now the inverse. So I form the inverse. This is the function. This is the inverse. Because that I need to make f the subject based on the instruction here. Let's say expressed in terms of x. So we need to transpose and make this the subject. To make that the subject, we transpose everything away from it. Take this 2, bring it over here first and subtract it. And then after I do that, you take this 3 and divide it under. That's simple 2 steps transposition. Very common. So we're going to end up getting x minus 2 first. When the 2 goes over, it becomes x minus 2. When x gone over, I'm going to be left with 3f to the minus 1. I need to get rid of the 3 and so divide the 3 under here. So I'm going to divide the 3 under here now. That leaves me with the f to the minus 1 by itself. So this is f to the minus 1 of x really. So I can write i.e. that is f to the minus 1 is really x minus 2 over 3. That's what it is. Because I'm finished now, I can put it back off x at the end. Off x. So the same off x on my left half up here, so put it back down as now. And that is it. So this is my answer right here. Nice and easy. But I go to that? Simple. You want to go to one of the fraction ones? I mean, like this, if you want the inverse of this one. All right, if you want the inverse of this one, let's do it. More maths equals better maths. So you don't want the inverse of this one, right? Let's do it anyway. Same thing. We say g equals x squared minus 1 over 3. But that kind of function here now, we're going to assume, we'll make an assumption that because the quadratic function, what's at a higher level tells you that because the quadratic function will now have a smile like that. Right? And so it would be a minute to one function if it's a whole graph. You'd have to use only half of it. And that's half or this half. But let me not get into that. I'm just going to take the positive square root. So this is over 3. All right? This is over 3. And then we're going to inverse this again. Inverse it. This g is going to become x equals. And this x is going to become g to the minus 1. So g to the minus 1 with a square on it. Minus back this one here so, and put it all over 3. I now need to make this a subject. I will transpose everything away from it again. First step is take this 3 and multiply it up here so. Cross multiply. Let's go step by step. I'm going to 3x equals g to the minus 1 squared minus 1. Take this minus 1, carry it over now and add it. Comes a plus 1 over here. So you get 3x plus 1 equals g to the minus 1 squared. To get rid of this square now up here, so we have to square root both sides. But I'm just going to take the positive square root alone. So we have a square root this side and also square root this side. When you square root a square, it cancels away the square. And all of that gone. And it becomes g to the minus 1. All right? I'm just using the positive square root. So imagine that we have square root at this side, the square gone, and the square sign gone. So I'm going to end up getting the square root of 3x plus 1 equals g to the minus 1. And I can put it back off x now. So it really becomes that this thing equals that. G to the minus 1 is now equal to square root of 3x plus 1. And I can put it back off x at the end. Put it back the off x right here. That will be it. If I do the inverse of g. Or do the inverse of the g. Let's set up a rational function and do the inverse of a rational function. Because when they set the rational function once, people tend to have a little bit of problem sometimes. Why? Because it's not frequently set. Right? And people don't practice enough. And let's set up a thing there. Let's finish this first and then we'll set up a rational function one and let's practice, right? Let's finish this. It wants us now to do g of f. So remember, g of f, it means f into g. It means the f1 into the g1. Let's set it out how it will work. So remember now that the f is equal to, or the f equal to, equal 3x plus 2. F equals 3x plus 2. And the g was x squared minus 1 over 3, right? X squared minus 1 over 3, right? X squared minus 1 over 3. And I'm trying to form g of f. So we said g of f of x. Remember what it means? In simple terms, it means you're putting the f function into the g function. That's what it means in simple terms. So you're taking all of the f function, taking all of what the f is. I'm going to take it and put that in the g function wherever the x is. So this is the only place that has an x in it. So you're going to make that construct. To make the composite function construct that the curve adjustment there. All right? So you're going to go like this now. So it's going to become equal to. It's going to have the 3x plus 2 where the x was. And put back the square on it. You subtract back this one out here, so. And you put that all over this 3. Everything going over 3. All over 3. That is it enough. So we have formed the composite function here. That's G of f. But CSEC wants us to simplify it down to look like this. So they don't just want us to leave it like that. So you'd have gotten a mark for doing this already. What's marks the value? Let me see what's marks the value. 4 marks. Wow. So you maybe get 2 marks to do that. And then 2 more marks to simplify it. So to simplify this correctly, you're going to have to expand this perfect square correctly. So remember, when you expand a perfect square, you don't get 2 terms, guys. You get 3 terms. Plenty people make the mistake of squaring this and squaring that alone. That is wrong. When you expand a perfect square, you get 3 terms. You get the first term squared. Then you get twice the product of the 2. You multiply these 2 things and double it. And then you get the second term squared. Let me do it. So this perfect square here becomes, pay attention, becomes a 3x squared. Where squared 3x, it becomes 9x squared. You square the 3, you get 9. And you square the x squared, you get x. Then the middle term is twice the product of these 2 things. How you do that? You multiply them first. You're going to get 6x. And you double the 6x to 12x. So the middle term is 12x. When I'm going to get 12x, multiply them first. And then double what you get. It's English language that. Multiply them and then double it. So when I multiply 3x and x, I get 6x. And I take the 6x and double it to 12x. That's how you get the middle term. And then you add the second term square, which is 4. That's what I got when I expand that bracket. Minus back the 1 over 3. You know, when multiply 3x times 2, what you get? 3x times 2x is gone. And you have to double that way again. 12x. Let's do another one. We're supposed to know this already, you know. I beat it, I bring my do this to come to class, you know. Graduation last year, you know. Let's do another one. 2x minus 5 squared equals what? First term squared is 4x squared. Twice the product of the 2. Listen. Twice the product of the 2 means multiply them first and then double what you get. So when you multiply them 2 things, you get negative 10x, and double that to negative 20x, negative 20x, negative 20x. Then the second term square is going to come at 25. Because negative 5 square becomes plus 25. Let me go back to know how to learn over everything from scratch. Let me go back and show. If you have, should not do the same now, but anyway, if you have a plus b, if you have a plus b all squared, let me go back from basics and show you again. A plus b all squared is the same as a plus b times a plus b. Okay now. How do I multiply this? I take the a and I multiply the 2 of these things, and I take the b and I multiply the 2 of them as well. See that? Good. Let's do the first one. So the a times a first is a squared, don't it? Then the A times B is AB, don't it? Then the B times A is BA. But BA is the same as AB, don't it? And then the B times B is B squared, don't it? See that? So see them not in a lie. It's 2 times the product of the two things in there. So 2 of them, see? Multiply the A times the B and then double it. Because it's 2 of them you end up with. See it now? Know it. Now for waste time and do this foolishness, so that's a waste time. So we have a perfect square to expand. Because if you look now, if you simplify this, it's gonna become this. Look, it's gonna become this. The first term squared, 2 of this, plus 2 times AB. So we do multiply the A times the B and then we double it. That's why I do that. Multiply the two things and then double it. Because that's what the midterm is. And then the second term squared, this is the second term squared. See, it's a B squared. You're not telling a lie. First term squared. This is twice the product of the 2. And then this is the second term squared. First term squared, twice the product of the 2. See that? Twice the product of the two things. English language matter. Second term squared. How do you do twice the product of the two things? Multiply them first and then double what you get. That's how you do twice the product of the two things. Multiply them first, then double what you get. If it was a minus, if it was an A minus B, no problem. All that happens that the middle term becomes negative. That's all that happens. So you follow the same process. First term squared is A squared. Then twice the product of the 2 is 2 things about B, a A, and a minus B. You multiply them first again, minus AB. Double it to minus 2AB. Then the second term squared. If you square negative B, you're going to still come positive B. So the third term is still a positive B squared. See that? So applying that now to this thing up here. So let's do it again. More math equals better maths. Let's do it again. So you see when I diagnose about the topic, I'm come for though. First term squared. You square this first. That's 9x squared. 9x squared. You square the 3 and you square the x. 9x squared. Then twice the product of the 2. How do you do twice the product of the 2? Multiply the two things. You multiply them first. 3x times 2 is 6x. Double 6x to 12x. So the middle term is 12x. Then the second term squared. 2 squared is 4. That's what I get from expanding that perfect square. That is it. But 60 wants us to simplify down to that. Factorize it down and think. Right? So we need to work this out and put this as 9x squared plus 12x. Watch this now. It's going to become 4 minus 1 is 3. See that? Plus 3. This is 12x. This is 12x. That is better, Mr. Shaw. Plus 3 and then dividing that by 3. When each of these can be divided by 3, you follow through and divide each of them by 3, right? So divide each of them by 3. You're going to get 3x squared plus 4x plus 1. And then this factorizes. They want this as factors. See, they want you to factorize it. So this factorizes into 3x. Okay, this is factorized. And all the factors of 3x squared is 3x and x. And all the factors of 1 is 1 and 1. Don't it? And then everything positive, everything positive. So this is the factorize. It's only no method, nothing. That is it. Those are the factors right there. So this is the answer that I wanted. But good? All right, so that was that. All right, so I wanted to show you now inverse of a rational function, right? So let me add a page to this. And let's beat down here. This was not a question, but I'm just showing you, right? So let's say we had, because I don't know what's coming in the exam paper, they give you some time for that. Let's say we had a function f equals, we had a function f of x equals 3x minus 4 over 2x plus 5. A rational function. You want to find the inverse of that. Right? Same thing. You can call it f first. I'm going to about this. I'm going to call it f first. So, I'm going to copy it back. Young stop the talking now, man. You just come to the class with the talking. So see here, we're calling this f first. We're leaving off the affix and let's call it f. Some teacher just call it y, no problem. And we're going to carry out the same procedure of expanding this because of inversing it, but it have two x terms in it. And it's a fraction, so we have to expand out everything into separate terms first. Expand it out into separate terms. You don't want them to be dividing each other. You have to expand them out in separate terms. So you can group everything with f to the minus 1 on one side and group everything with x on the other side. So expand them out into separate terms first. All right? So let's inverse it. Inverse it as a first step. Inverse as usual as a first step. The same thing. The f becomes x. Somebody listen something. The f becomes x equals this x and this x. Each of them represent domain. They become range on the inverse function. It becomes 3 times f to the minus 1 minus 4 over 2 times f to the minus 1 plus 5. And then you have to transpose and make this f to the minus 1 the subject. Now, wow, get one term with f to the minus 1 on the subject. So if I expand out and put everything with f to the minus 1 on one side. First step is to take this denominator and multiply it across it by the x. That's the first thing we have to do. So we expand it out. That's always the first step. Expand it out into separate terms. So we're really doing the x times this and the x times that. We multiply it across. Good? All right. So it's going to be x times this first. So we're going to end up with 2x f to the minus 1. And then the x times this is going to become a plus 5x equal. And this remains on the right side. 3f to the minus 1 minus 4. But I'm going to far. Then all the terms with f to the minus 1, because I want to make it the subject, I want them on the same side. So I need this and this to be on the same side of the equation. And I need this on the other side. So I need to take this over here to join with that. And take this which don't have any f on it over this side. All right? So I'm making those simple transpositions. So this stays on this side. 2x f to the minus 1. This 3f to the minus 1 comes over here and becomes negative minus 3f to the minus 1 equal. This negative 4 stays over there as a negative 4. I never move it. And you have to keep the negative on it. Negative 4. And this positive 5x comes over and becomes a negative 5x. Negative 5x. Everybody good so far? In order to have these terms with f to the minus 1 on the same side, I'm going to factorize the f to the minus 1 out of the two of them. Factorize it. All right? So I'm going to factorize the f to the minus 1 out of the two of them. So I'm going to have f to the minus 1 factor out of this gives me 2x. Factor out of this gives me negative 3 equal. I don't change anything there. So from negative 4 minus 5x. But I go so far. Then to leave this by itself as a subject, I'm going to take all of this thing and divide it on this side. Take all of that thing and divide it. And so I'm going to get f to the minus 1 equals minus 4 minus 5x all over 2x. Youngster, stop talking, man. One tear, man. Minus 3. That is it. All right? And now that we're done, put in back the offense. Somebody playing something. I keep hearing something. Huh? Hold on. Come on.
Sir, this here. It's our meet at the meeting over your pool, sir. Sir, sit down. The me try to say, I don't tell you. Yeah, idiot. Oh, okay.
All right, let's go. But I understand that. You all need to look back at the video and practice this type of function. When I give this type of function, a lot of people mess it up. The rational type, and I give it from time to time. You only need to be able to do one of them and do the same steps. These are the same steps to transpose this. All right? Same steps to transpose it. Take a screenshot of it and I'll practice it over again. You know, when I say I do 1 million of them, I do 1 million of them already. What's more me for do? I won't have to do them now. Should be doing them already. You don't know what's coming on the exam paper. It come in the past, it come multiple times, it can come again. This type of function. Depend the inverse. We don't know what's coming on the exam. But we prepare for anything. We don't know what's coming on the exam paper. So you prepare yourself for anything. And especially things that you know, giving a challenge, you know it should not give a challenge. You work on it and get the challenge out of it. You don't leave it to remain challenging for you. You practice a couple of them, it's a simple 1, 2. Simple 1, 2, just your ability to transpose. That's all that this is. How well can you transpose? All right, that is it. I remember this function is undefined if the denominator is 0. Right? A rational function. It's called a rational function. It comes in the form of a ratio. It's called a rational function. It's undefined. When 2x plus 5 is 0. And the denominator can't 0. Can't divide by 0. That's when the x equals negative 5 over 2. You over the 5, you get negative 5. And then you divide the 2 under it. So x equals negative 2, negative 5 over 2 cannot be in the domain. Cannot be in the domain. This value cannot be in the domain. Cannot be in the domain. You don't want this value in the domain. Because it will not have any value to map onto. Because if the x equals negative 5 over 2, this honor is going to be 0. You can't divide by 0. So you cannot have that value in the domain. Otherwise, the function cannot work. If that value is there, it's no longer a function if that value is in the domain. But that's not good. All right. What is it on this paper to do? So I have to put it in again. Quadratics. So with the quadratics on this paper, with the functions on this paper, and with the transformation on this paper. So we'll go to this paper, right? All right, let's do another paper. Let's do the January 2015. Let me see. Let's do the January 2015. Let's do the January 2015. Let's do the January 2015. Some of the older questions better than all these questions. Right? Some of them better. Learn more from them. Some of the older papers. Let's see what I said on this one. January 25th.
Yeah.
I like to see simultaneous equation with a line of curve. Stuff. And mute the mic, please. Somebody mic is open. Mute the mic, please.
You know, 4 from.
Or is this no? Nope. Here's a transformation. It's easy enough. We can fast. I want us to get a couple of matrices type. We have to actually calculate our matrices. Transformation. Right? Let's see. It said the diagram below shows triangle LMN and PQ. I don't like when they give different letters. So I have to now focus and recognize that the L go to the P, L going to P. Just to make sure. The L go to P, the M go to Q, and the N go to R. Alright? Because this go to that. So match out the letters then properly. Alright, so go to PQR after transformation. So it is which one to which one? This one to this one. That's clearly a translation. You can see that? No turning, no change in size, no rotation. The thing just move from one location to another. That's clearly a translation. Alright? It's clearly a translation, that one. This to this. It says right on the corners of N. N is this point. Right up here. That's 4, 5. Put the x value first. Put the horizontal dimension first. Horizontal coordinate first. 4 across, 5 up. So the point is 4, 5. Coordinate is 4, 5 like this. 4, 5. Next one. On the grid, draw triangle. Draw a triangle FGH, reflection of LMN. Reflection of LMN. See, you know, different thing again, you know. Right, we got the same method anyway. So we're going from F, we need FGH from LMN. So again, we have to match up the letters, right? So in this example, the L is going to F, the M is going to G, and the N is going to H. So we can make sure, right? Label them the right way, everything important. So we're doing this triangle. How we're doing it, what them supposed to do? Reflect it in the y-axis. Instead of saying the y-axis, they could have said the line x equals 0. You know that, right? The y-axis is a line x equals 0. CSEC been doing that in recent times. Instead of just saying y-axis, they say line x equals 0. Instead of saying x-axis in another question, instead of saying x-axis, they instead say line y equals 0. The line y equals 0 is the x-axis, and line x equals 0 is the y-axis. So look out for that, all right? So reflecting in the y-axis, guys. So reflecting this triangle up here in the y-axis. So the y-axis here, so that's a mirror line. Remember, do it one point at a time. Image distance equals object distance. So the L first, the L going to F, L going to F. So the L is 2 units to the mirror line. It's going to go 2 units on the other side to here, to here. So that's where the F is going to be, L going to F. Next point. Next point is M going to G. M going to G. Where is M? M is 1, 2, 3, 4 units of the mirror line. It's gonna go 1, 2, 3, 4 units on the other side to here. So M going to what? M going to G. So right here is gonna be the G. And then the other point, N. N going to H up here. H. H is 4 units to the mirror line. It's gonna go 4 units on the other side as well to H right here. H. So if you notice, I've done my reflection 1 point at a time. Now that the points are in place, I'm gonna draw the triangle now. Draw the triangle. Now that the points are in place, I'm just gonna draw my triangle. Join those 2 points, join these 2 points, and join these 2 points. That's my image triangle right here. Nice and easy. Make sure you label them properly. Everything important. All right. Next one I want us to do that. Use vector notation. Describe transformation that maps LMN onto PQR. LMN to PQR. That's this to this. Easy. That's a translation. And they never go left or right. You just go vertically downwards alone. So there's no horizontal movement. So the horizontal component is 0. And the vertical component is count. Don't get it wrong enough. Don't do this point to this point, and that will be wrong. This point went all the way down to here. Safe point to use is this one down to this one. Just count how many units down. And when you're going to count units, don't just start counting boxes. Because sometimes 2 boxes make 1 unit. Look out for that. So you're going to count the boxes and say what 1 box is. How much unit 1 box is. In this example, 1 box is 1 unit. See there? 1 unit. From here to here is 1 unit. From 1 to 2 is 1 unit. So each box is a unit. So it's 1, 2, 3, 4, 5, 6 units down. That's a negative 6. If 6 units down, it's negative 6. So the vertical component is negative 6. So that's it. That's a matrix right there that I want. 0, negative 6. 0 because it did not go left nor right. It only went 6 units down. So the vector component for the translation is 0, negative 6. It said describe transformation L to N. It's a transformation. So we give the name of it to them. It's a translation. So we're gonna say a translation. Translation. That's the name of it. I give the name of it. Translation given by 0, negative 6. That is 6 units downwards. Only did 6 units there. If you leave this, I give you a marks. They're looking for that. So looking for the word translation and looking for that. Give them those two things, you're good to go. Because if you describe a transformation, you have to give the name and the components. And they tell you that they want a component in vector form, vector notation. This is what they call vector notation. All right? Very good. Next one, it says complete the statements. PQR is mapped onto PGH by a combination of two transformations. Let's look at it. So it's PQR to FGH. PQR to FGH. Let's look at it. PQR, PQR to FGH. I don't know. It's this one to that one by a combination of two transformations. The glide reflection, listen. PQR to FGH. What happens? Two transformations. We can say that translation up back this of 6 units up, and then a reflection in the y-axis. But I can say that. See it? Or we could do the reflection first. A reflection in the y-axis first, and then 6 units up. You see that? See it? Same thing. That's what we call a glide reflection. We have a translation, and then a reflection in a mirror line, and the mirror line is parallel to the translation direction. That's what we call a glide reflection. You youngster, I'm going to send you home. You call your father tonight, enough for sure, enough. They have a sickness, I tell you. If you get rid of it, make your father help you get rid of it. All right, so see it you know by a combination. So PQ is mapped onto this, I will just figure it out by a combination of two transformations. First, PQR is mapped to LMN. See it? PQR goes up to LMN by a translation. Translation. I'm saying parallel to what? I'm going to say 6 units. I'm going to give them everything. 6 units up it goes. So I'm going to say 6 units. That's translation. 6 units. 6 units. Parallel to the y-axis. I go parallel to the y-axis. Parallel to the y-axis. I go 6 units parallel to the y-axis. Then LMN is mapped onto FGH. Then LMN is mapped onto FGH by a reflection in the y-axis. By a, you know, by a reflection. Reflection in the y-axis. See that? See? And that is what we call a glide reflection. Let's put it there. I.e., that is a glide reflection we just did. CSEC could ask what the name of it. I've done it before. Last time I remember they gave a question like this, they went on to ask a part and said, what's the name of this time of compound transformation? It's a glide reflection. We have a reflection in a line in combination with our reflection. We have a translation in combination with our reflection in a line, where the line is parallel to the direction of a translation. Mirror line is parallel to the direction of a translation. It's called a glide reflection. And it don't matter which one you do first. You can do the reflection first, then the translation. I can do the translation first, then the reflection. The result is the same. called a glide reflection. It says these two triangles are congruent. What congruent mean? A congruent mean? Congruent means same, equal in every way. It's a fancy word for same. They are equal in every way, dimension-wise. State two reasons why they are congruent. Simple. All sides equal. All the sides are equal. All sides are equal. And all angles are equal. Everything equal. All angles are equal. So the sides are equal and the angles are equal. That's why they are congruent. They have equal perimeter, equal area, equal everything. Congruent. Congruent is a fancy word for shape. Congruent shapes are the same thing. Like if you have two circles with the same radius, them two have the same radius. Come on. Congruent circles that. Congruent circles that have the same dimension, same radius, same diameter, same circumference, same area. Congruent circles. Congruent is just a fancy word which means same. All right, it's not complicated. Let's look for another question on this paper. Is how we're doing today. Let's see what else is there for us. I want to give a break after this one, short break, and we'll come back because I want people paying attention. All right, short break, and we'll come back and spend the last hour. So we can do some of the more recent questions. I see a function here again. More of the same, guys. The question are easy, you know. They give you F and they give you G. Another one, F of 7. We're going to put the 7 there first. All right, so the simple becomes 5 times 7 minus 4 divided by 3. 5 times 7 is how much? 35. 35 minus 4 divided by 3. That becomes 31 divided by 3. That's it. Very good? Then I want F to the minus 1. Same thing again. I want the inverse of this. No problem. Say F equals 5x minus 4 over 3 first. 5x minus 4 over 3. Call it F. Huh? Why you put a decimal if you have that? Where you go on? Where you waste time go on the calculator? Look, we waste time. Where about waste time go on the calculator? Work told for why? Where again? You lose time. You're not getting anything. You're losing time. Just leave it like this. Listen, you must use the calculator as minimum time as possible. You know, get no more mark or no less mark for work this out. So we about to work it out for. Just leave it like that. They didn't tell you how to express it. Leave it like that. They will give it. Look here. They will want to give you the marks, you know. CSEC, they're so anxious to give you marks. You know why they will want to give you the marks? Why they want to give you the marks? Huh? No, because so many people getting them wrong. The markers frustrated when the marking exam, you know, because 70% or more of people writing foolishness. So they get somebody who do something right and near right. They're happy. They're glad to give you the marks. Because whole day they have to be a mark wrong. When teachers marking paper and see people are right foolishness, it's frustrating, you know. So when you give them one thing and you do something right, they happily give you the marks quick and fast. You just want to look right and then give you the marks to right. Right? So you don't need to go touch calculator for work that out now. You give away time. You waste time for work that out now. Not gain nothing, not lose nothing. A 1 mark for it, you know. 1 mark for the answer then. You do additional work on it for. Come on, man. Smart, smart. You go work that out with calculator and waste time. Use the calculator only when you have to in the exam room. In the exam room, you really only use the calculator for the first question and the tricks question. You can do the whole paper with no calculator. You smell a calculator up here? You can do the entire paper almost without a calculator. The more times you use a calculator, the less time you spend on the paper. Use the calculator only when you absolutely have to. Come on, man, you have to work this out for no reason, man. You're not getting nothing for working that out with no calculator. Leave it like that. So, let's go. Well, inverse this now. So inverse it. Set it up first and then inverse it. Inverse it. The f becomes x equals 5 times. The x becomes f to the minus 1. Minus 4 over 3. Simple. All we need to do now is transpose and make it a subject. Transpose everything away from it and leave it by itself as the subject. We're going to move this 3 first. Multiply and cross here first. Cross multiply. To learn this basic transposition. Can't teach us now. Perhaps put them do this. This is 3x equals 5f to the minus 1 minus 4. The 3 gone. I want to leave this by itself. What am I going to do? Go over the 4 first and add it, and then take the 5 and divide it. And same transposition all the time. Practice it becomes like second nature. 3x. Go over the 4 and make it positive. Positive 4. Take the 5 that is multiplying and divide it under this side. Over 5. That leaves with f to the minus 1. That's it. And you can turn it on if you want. You can say, i.e., f to the minus 1 is this same thing. 3x plus 4 over 5. And put it back off x. No, you don't. Put it in back off x. That's it. That's the answer. Very good. What else? The more f of g. The more f of g now. Let's write what there so we can construct and show you again. So remember now the f is 5x minus 4 over 3. The g is x squared minus 1. Let's copy them though. We can show the construction one more time. Where you construct this composite function. So remember now, don't give away this. Them question too easy for you to get wrong, you know. You put in the G into the F. Remember that little thing we draw all the time and do it. The G into the F. You're taking all of the G. And you put it in the F wherever X is. Right there. That's the only X in there. If there's another X in there, someone will put it under there, so 2. You put it anywhere X is in the function. That's how you put substitute F into G. Simple. Do that. Construct that and you have the composite function. Therefore, f of g of x equals, construct that something that we just draw out a while ago. Put back the 5 first. Where the x is, you put the whole of the thing in red there. X squared minus 1 where the x is. Put back the minus 4 beside it, minus 4. Put back everything over the 3. Put back everything over the 3. That is it. That's it. You might want to simplify it, but it can be simplified. Right? So I'm going to expand out this first and get 5x squared minus 5 and then minus 4 right there. So minus 4 all over 3. Minus 5 and minus 4 makes minus 9. It's 5x squared minus 9 over 3. But that's submit to you. Maybe if you leave this, then get your marks same way. Right? But because I see 2 marks there, I say, okay, let's assume that is 1 mark for form it and the other mark for simplify it. That's what I just simplify it and do. So sometimes I put an eye upon it. See, if this was 1 mark alone, right? So don't write this, you know. Don't. But you must still practice to simplify, right? You're expected to simplify. So I'm going to say the right thing, Mr. Shaw. You are expected to simplify expression. All right? You are expected to simplify. Give your answers in simplest form. That's what you're expected to do. All right? So let's continue. This one, we want us to go from this to this. Let's use the formula method. It's good time to practice. Already know. So when I teach advanced, I teach this a different way. Right? But for CSEC, over the years, I found that it's better to use the formula method to do it. So instead of using this, guys, we're going to use a into x minus xt squared plus yt. We're going to calculate the xt using minus b over 2a. What is the a and the b? We get them from the standard form up here. Let's write them out in red. The a is the coefficient of the x squared term, which is the 3, the number in front of it. You open the x on it, you know. if it was just x squared alone, then the A will be 1. When there's no number in front of the coefficient is 1. A and B and C are constant values. You can't put expand the A, the B, and the C. So you can't say 1x is A, or the A is just a number, coefficient. All right, so this example, the A is 3. The B is the number in front of the X, which is this positive 6. The C is the constant term, which is negative 2. You have to carry the negative with the C. You can't just put 2 alone. It's negative 2. And we're working on xt now with those values, those 2 values. So this is going to work out to be minus the B is 6. The B is 6 over 2 times A. The A is 3. So you get negative 6 over 6, which then is negative 1. Negative 1. So the A is negative 1. So negative 1 is coming right here for the xt value right this. Let me shift this to a little bit. So this negative 1 is going to go where the xt is. So the minus is going to come a plus in the bracket. So you see, if it's supposed to become a plus, it works out the same to become a plus. But the x value at the turning point is still negative 1, even when this in here becomes a plus. At least you know what the x value at the turning point is. It is this, negative 1. Forever and ever, amen. Then yt, when this works out to be a whole number, you can find yt by plugging the negative 1 in the function there. So you can get yt that way. We can get the formula as well. I'm going to do it 2 ways this time. If I'm doing this exam, I'll get my yt simple by putting the negative 1 there and done. But I'm going to do it the 2 ways just to show you this time. We use a formula to do it and then also to plug it in there. So the yt is 4ac minus b squared over 4a. Plenty of people make the mistake and put 2a under here so all the time. Because remember the quadratic formula. Yt is 4a under there, not 2a. Pay attention to the details, everything important. If you're going to use this method, learn the formula method properly. If you want to use this method to do it. Plugging in the values now. 4 times a, the a is 3. Times c, the c is negative 2. Minus, remember this minus is this minus, it's not squaring, you don't square it, it stays minus. Then the b is 6, so you're squaring the 6. All over 4 times a, the a is 3. And just if you simplify that down. All right, so this becomes equal to, this is what? And this is 12 times 2, that's 24, that's negative 24. Minus, that's this minus and that square, stays minus. I'm only squaring the 6, so that becomes a 36. And that divided now by this is 12. What have we worked out? Huh? Negative 5. Thank you very much. Let's get the negative 5 another way I'm going to show you. Or, we could instead do yt equals, plug the negative 1 in this to get yt. Get the same answer just to show you. So you have a choice. So you want to do it. To be 3 times negative 1 squared. See? 3 times negative 1 squared right there. So plus 6 times negative 1. See there? 6 times negative 1 right there. Minus 2. Where the sum? The negative 1 squared becomes positive 1 times 3 is 3. This becomes a 3. 6 times negative 1 is negative 6. Then that negative 2 right there as well. That's all negative 8. 3 minus 8 is negative 5. Same negative 5. So let's get the same answer. I'm doing it this way. I will do it this second way. Let us just do it. Because I did that. Once I did that whole number for my xt, then I calculate yt that way. But you also have the formula with it, your choice. Now that I have xt and yt, I'm plugging them in this. I'm plugging them in this thing. Right? So this thing now becomes, look at it. This thing now becomes f of x. They call it f of x. They call it f of x. It's now equal to a in front. The a is 3. See there, the a is 3. 3 bracket x minus the xt is negative 1. So you're subtracting a negative 1 minus 1. Don't forget to put on the square. People always forget to put on the square. Then the plus yt is negative 5. The plus yt right here is a negative 5. Let's put minus 5. This minus in here becomes a plus. I can rewrite it as 3 into x plus 1 squared minus 5. That is it. Very good? That is it. Next part now say, hence or otherwise take the minimum value. The minimum value is a yt value. The minimum value is a yt value, which is equal to negative 5. It's not complicated. The lowest y value on the graph is a y value, the turning point. The lowest y value. The function gives you y values. And the lowest one I give you is the yt value. If there's a frown, it will be a maximum. If the square term was negative, same thing. It will be a maximum value, will be the yt value. Take 1 mark for that. State the equation of axis of symmetry. Axis of symmetry is always x equals the xt value. What is xt? Xt is negative 1. So the axis of symmetry is x equals negative 1. That's the answer. X equals negative 1. Too easy. And the x value turning point is negative 1. The minimum point, you don't want it, the minimum point. The minimum point would be xt, yt. T means turning point. That would be negative 1, negative 5. Negative 1, negative 5. Because xt is negative 1, yt is negative 5. Negative 1, negative 5. You don't want us to sketch it? Sketch it. I want us to sketch it now. So what do we know about this graph? The A is positive, so it's going to have a smile shape. The A is positive, so it's going to have a smile shape. Gonna smile. Gonna have a smile shape. Because the A is equal to 3, and that's a positive value. The y-axis intercept is 0c. 0c. C is negative 2, so that's 0, negative 2 is where we cut the y-axis. The minimum point, we said already, it is xt, yt, which is negative 1, negative 5. We need to put all these information together now on one graph. Let's be smart about it. It's a sketch you're doing. It's a sketch. You don't need no scale. Anything like that. It's a sketch. So I'm going to put in a line for the y-axis like this. Put in a line for the x-axis like that. Now I'm putting my x-axis further up. Why? Because I know that this point is further down. All right? All right. So let's go. So when it's going to have a smile shape like that, when we put it to turn at the right place, it turns here. Where would that point be? Negative 1, negative 5. Where the x value is negative and the y value is negative. That's over here. Right? Over here. See, negative 1, negative 5 is somewhere down here. So it's a turn somewhere down here. So that's what we know. It turns somewhere down here. The next part, next thing. Where would this point be? 0, negative 2, the y-axis intercept. 0, negative 2 must be down on this part of the y-axis. 0, negative 2, somewhere down here. So we need a smile that turns somewhere down here and crosses the y-axis somewhere down here. Let's draw it in red. So, would this be correct? Because the turn is at the wrong place. Would this be correct? Would this be correct? Would this be correct? Why not? Why is not correct? You turn at the right place. It's right, but it's wrong. Cross works at the wrong place. See that? If I combine everything. So you want it to turn down here and cross up here. So let's draw that. So draw something like this. See there now? Draw something like that. And yes, and the thing get them. Let's do that. This is such a yeah, something like that. There's lay beam. So I'll put this point as my minimum point, -1, -5. These are my y-axis intercept. 0, negative 2. Give them that. Get them. Can I shift it over a little bit? Let's shift it over a little bit. Let's shift it over a little bit. Let's shift over the y-axis a little bit. So put in this point further over here. Not to scale, so it doesn't really matter. But 0, -3. That's it. But I got that. That's all I wanted. I wanted the roots, you have to find them 2 points here. Roots. You have to find X value there and there. But I don't want it. This question wasn't about roots. This question was about turning point. Alright. That's it. Alright, question done. I think we're done with this paper. I'll take a short break. Anything else? So we'll do on this paper, we'll do transformation, we do function, or do quadratics, right? I'm gonna do a simultaneous equation for you. I'm just gonna do the normal way, this one. You alright with this type? You alright with this type? Is a line and curve that I have a problem with? Line and curve. Alright. I'm still can find one. I'll do it after the break. Alright. I just need to see one of them doing it. This is a substitution method. Alright. I'm gonna find one quick and show you. I'll find one. Must can find one from the notes. I'm gonna find one. Hold on. So we did it in quadratics. So we did the topic of quadratics. That's how we did it. Quadratics. Let's find an example here. What? Can I find one? Line on curve. Line on curve. Line on curve. Alright, see there, line on curve, right? Some examples there, so. There you go. Come back. Alright. Let me pick one for you. Let's say we have um let's say we have let's say we have this. This have simultaneous. Let's say we have let's say we have y equals x minus 4, and we have y squared plus 17 equals 2x squared. Now, generally speaking, we have a line and a curve like this. Right? You know the curves. Curves are the ones that has products and quotients of the x and the y. The line are the ones that can be written from y equals mx plus c. So this will be the line. and this will be the curve. All right. Now, generally speaking, we have a line and a curve to solve simultaneously. A safe method to use is the substitution method. Then to substitute the line equation into the curve equation. And I get a quadratic. All right. So because this one already has y as a subject. This one already has y as a subject. Okay, what it is, you know, at the point where the line and the curve intersect, the y value on the line and the y value on the curve is the same. Because like you have a curve, you have a line. At the point where they intersect, the x and y value on the curve at that point, and the x and y value at the line and the curve at that point is the same. So you're trying to find the points where the x and the y value on the curve and on the line equal. They're the same at these points. So you do the same thing with the mathematics. You make the y value here and the y value here the same. So you equate them. Get me? You equate them in a sense. So at the point of intersection, the y values are the same. Now the line is saying the y is equal to x minus 4. So the x minus 4 that the line is saying y is equal to can be substituted for the y right here. That's why you substitute it. But you want to establish an equation with only one variable. So we're going to substitute the line into the curve for y. That's what we're doing. Sub the line into the curve for the y value. So we're going to get an equation with x alone. When you find the x, get an equation with x, it's going to be a quadratic. Why is it a quadratic? Because there are 2 points of intersection. CSEC will only give the type where there are possibly 2 types of intersection. There are situations where you can have 3 points of intersection. That would have to give you a cubic equation with an x cubing. CSEC not giving you that. It's above the level of CSEC. CSEC is only giving the type that will lead to a quadratic because you're not getting any more than 2 points. Get me? Good. So when you just put the line and the curve together to find where they intersect, you're going to end up with a quadratic. And when you solve the quadratic, you get the 2x values. So 1 for here and 1 for there. All right? So I want to solve now. So I want to do this set up this substitute the line to the curve. Where the y is, I'm going to write x minus 4 squared plus 17 equals 2x squared. I need to expand this out and set it out like a standard quadratic equation so I can solve it. A standard quadratic equation is one of the form ax squared plus bx plus c equals 0. You want to get it equals 0. So you can solve it using either factorization or quadratic equation. All right? That's what you want to do. So we have to take this equation now and simplify it and bring it down to that form. Standard quadratic equation form. So expand this first. Remember, it's a perfect square. Remember, perfect square expand out into 3 terms. First term squared, twice broken over 2, second term squared. If you expand this wrong, your answer will wrong. Get me? So we do everything right. We just did the perfect square one. So the first term squared, can't go forget it now in the exam next week. First term squared is x squared. Then twice the product of 2. Always we do it again. Multiply them first. You get minus 4x and double it to minus 8x. So the middle term is minus 8x. Then the second term squared is positive 16. Remember, if you square negative 4, we're going to come positive 16. Same thing. So the third term is a positive 16. Don't go put the negative 16 there, you're just dead. It's positive 16. By you're squaring the negative 4. Not the squaring the 4, you're squaring the negative 4. Remember, we expand it at x minus 4 times x minus 4. It's minus 4 f times minus 4, you know. That's what you're doing now. You get me? Good. So it's minus 4 squared again. And then put back this plus 17 now equals 2x squared. They try to simplify it. So I can take all of these terms and bring it over here. Why am I bringing it over here? Why don't I bring this over here? Because if I bring this over here, I'm going to end up with a negative x squared. Quadratics are easier to handle when the square term is positive. So I'm going to always transposing a way to keep my square term positive. Do the mathematics the easy way. So instead of bringing this over here, I prefer to take this and carry it over this and subtract and keep my square term positive. Everything have a reason. All right? So I'm going to keep my square term positive. So ready now. Equals. I'm going to take this over there so and subtract it. 2x squared minus x squared give me just x squared alone. But I go to that. Take that minus 8x over there, so carry it over there, so and it becomes a positive 8x. Again, plus 8x. This and this add up too much. 33. 33. So take this over here, that become a negative 33, don't it? Minus 33 equals 0. See that? It is the same as x squared plus 8x minus 33 equals 0. I'm going to factorize this now. Equals 0. The only factors of x squared is just x and x. You want factors of 33 now where the difference is 8. That's 11 and 3, don't it? Don't it? 11 and 3. 11 and 3. Two signs in the bracket are different. Give the greater product the positive sign. The greater product is this one. Greater product is this one. That's 11x versus 3x. Make the 11x positive and the 3x negative. Remember, it's the far product and the near product that gives you the middle term. But you could go to the normal factorization process if that's what you have to do. You get me? So anyway, those are the two factors. So then this factor equals 0 means that x is equal to negative 11. And this factor equals 0 means that x is equal to 3. Those are the, I put negative x, negative 11 in the short. These are the two x values where the line and the curve meet. I need to find the corresponding y values now, as I'm finding coordinates. How do you find the corresponding y values? Always substitute them in an easier equation, which this time is the line equation. The one that will give the y values easier. Get me? Substitute them in the line equation. So you're going to substitute them in the line equation. So sit here, you're going to substitute them into the line equation, which is y equals, what is it again? X minus 4. You're going to plug x equal minus 11 there first. When x equal minus 11, the y becomes minus 11 minus 4. That's negative 15. See that? So 1 point is minus 11, negative 15. That's 1 point. Minus 11, negative 15. That's 1 point of intersection of the line and the curve. Other point is where x equals 3. Put x equals 3 in this as well. So when the x equals 3, y becomes 3 minus 4. 3 minus 4 is negative 1. So the other point is 3, negative 1. Other point of intersection is 3, negative 1. It means that the line and the curve intersect at these 2 points. This point and that point. Get me? The key step is this. Substitute the line into the curve and you get a quadratic equation. When you get a quadratic equation, it's not standard yet. You have to simplify and transpose it down to a standard. Transpose it down, make it become standard. This is what we call basic. That's a basic quadratic equation. Basic. A basic quadratic equation is the one that can be transposed and simplified down into a standard quadratic equation. Don't solve basic. Don't try to solve basic. Always solve standard. So you have a basic quadratic equation, you transpose it down into a standard quadratic equation. The standard one is where you have a quadratic expression equals 0. Because the method that we learn to use, to solve quadratic equations is based on when the quadratic is equal to 0. Right? Because when it's equal to 0, that's when you are able to use a quadratic formula. Because the quadratic formula was derived on the premise of an equation that is in the standard form. And then the factorization method is the one that uses that special property of the number 0, where if the product of two numbers equals 0, then one out of the two of them must be 0. One or the other must be 0. You get me? So that is why you could bring your quadratic equation to that standard form. So you can use those two options, the quadratic formula or the fact that products equals 0, one of them equals 0, one or the other is 0. All right, so that's why I have to bring it down to standard. So don't solve basic. All right, guys. What time is it? That's what time is it? All right. I take another short break. and come back and do another paper or two. And we're working up to 9. All right, so we have another paper hour. We're going to take like a 10 minutes break, and then we'll come back and just finish off with another paper or two. We say we're working up to 9 o'clock. All right? Huh? So come, put the clock on it. 10 minutes break, 10 minutes break. 10 minutes break. Huh? 8:30, break till 8:30. By the time we do 2 questions, 8:30 go pass. Something, man. You're lazy, you know, you're lazy, man. Exam around the corner, put in the work, my youth. Exam around the corner now. The exam is just around the corner. Nobody said no shortcut. I'm going to old, you know. I'm old, you know. I'm the one who's old. You're young. You're a young man. Stop acting like you're old. Complain too much, man. Help you now, I will not get help you now. I'm get help. Help me, I tell you, you know, brother, I go sleep and relax myself. Think I have to be doing this. I don't have to be doing this. I'm trying to help you guys out. But I want you to do well on the exam. Come on, man. Stop the foolishness. I don't have to be doing this at all. I don't have to be doing it. Doing it to help you. I want one of the past papers that the table. Join the graph. See. 2020. 25. Yes. Here comes last year exam paper. Where we do this question? Last year exam paper. So, you know, I say I want to do mathematics all day class next week from 9 to 9. But students are not serious, man. I do a mathematics all day next week. Yeah, we just do try and do 2 or 3 full exam papers next week. Next week, Saturday. Okay, maybe do Sunday to Saturday and Sunday. Mathematics all day for 2 days. Mathematics all day for 2 days next week. Saturday and Sunday. But you guys will cry. I get food. Somebody bring food for you? Who bring food for you? Come show me how to bring food for you. I go out with them and show me. Come show me how to bring. Yeah. Let's just do this. Last year exam paper, 2025, June last year. Online, can you hear me and see me? See the screen? I stuck again. Let me just stop it and start the back. Online, I can see and hear, see the screen and hear me? Okay?
Yes, sir.
All right, good. So this paper is the June 2025 paper. Then maybe do the January one as well. And then we'll call it a night. All right, so far this takes us. Time is it now? It's now, oh, it's 11 past 8. All right, let's see what far this takes us. So it's a recent exam, right? Last year. Let's go, let's go, let's go, let's go. All right, this is number 1. Number 2. All right, here's a transformation question. As I said, it's an enlargement. Right? Scale factor positive. Are the image and object pointing in the same direction, right? It's pointing up. It's pointing up. It's also pointing up. All right? Which one is the image? Which one is the object? Can be enlargement. If it's this way, the scale factor is a fraction. If the enlargement is this way, scale factor is a whole number. All right? Let's see what they say. They say the diagram below shows quadrilateral R and S, where S is the image of R under a transformation. So S is the image of R. So the transformation is this way. So when it's an enlargement, you can start pick up some of the information right away. So this side here was 1 unit and has grown to 2 units. So now the scale factor is 2 right away. Scale factor is 2 because one dimension has trouble. So only this is what happens to one dimension. Then where is the center of the enlargement? To find the center of the enlargement, you're gonna join corresponding points and extend backwards until they meet. All right. So, for example, you can join these 2 points, which are corresponding points. And we can join these 2 points, which are corresponding points. See where those lines meet. And after we see where those lines meet, we can check if the enlargement of scale factor 2 also affects distance from the center of that enlargement. You can find the center and just check if it is correct. So I'm going to join those 2 points. I know it's going to ask me for this, so I might as well just do it from now. So join these 2 points and extend it back. And join these 2 points and extend it back. I don't know. Oh, this line not so straight. You do it with your ruler, guys. Well, let me try and see if I can do it with this. So like the pen is wobbling. Let me see if I can do it better. So it's up to here, there. 1, 2, 3, 1, 1, 2, 3, 1. So it passed through here as well. So it's going up through here. And up through here. So the line goes up through there. Let me see. That line. And if we do the other point, this one and this one, see where it goes. So this is this point and this point correspond. So let's see. It's 1, 2, 3, 4, 5. 1, 2, 2, 3, 4, 5. All right. So it pass through here as well. I have to go working it up. This device not allow me to draw the straight line. Right? So I have to pass through here as well. But I'm going to straight and show you. So you join these 2 lines, these 2 points, extend that line. So the bit's going to go like this. That is it. And this can be extended further. So you see where those 2 lines meet? This point looks like it's the center of the enlargement. This point right here. Where those 2 lines meet. All right? And we can check if it is correct. Remember now, that scale factor affects distance from the center. So this distance is supposed to be doubled, which it does. That distance is doubled. Right? This distance to this point is doubled out to here, which is correct. The distance down to this point, this distance down to here is also doubled down to here. Because the scale factor of 2. So we can accept that this is actually center of that enlargement. All right, we have not started to answer the question here. I'm just figuring out stuff as we go. But you put your ruler against these 2 points, put your ruler like this against those 2 points, and draw the straight line. All right, to see where the those lines intersect, or where the lines go. All right, but that is it. Let me see what the question says. It says, describe fully the single transformation which maps R onto S. I see, that's the very first question. When it's an enlargement, when describing an enlargement, you have to give the scale factor and the center. You cannot just say that enlargement of scale factor 2 alone, that's not enough. You have to give the center as well, because enlargement has a scale factor and a center. And so the word fully here, very important. You have to tell everything about the enlargement. And the 2 main things are the 2 things about an enlargement, are 2 components of an enlargement, the scale factor and the center. We have found both of them. We found the scale factor by measurement, comparing size, like this one and this one, it has doubled. I find the center by joining corresponding points and extending back till the meet. Joining corresponding point, extending back till the meet. And so this is the center of the enlargement. We just need to state the coordinates of that center. What is it? That point is 3, 7, 3, 7. This point is 3, 7. So we can describe it now. So this transformation is an enlargement of scale factor equals 2. And center G7. I could say about the point G7. All right, that's it. That's all I want to see. If you want to list it, you can say enlargement, scale factor equals 2, center 3.7. If you even list it like that, they give you a marks. 1 mark for each thing. All right, name 1 mark. Each of the 2 components, 1 mark. That's how you get your 3 marks. All right, next part. It says on the grid on page 12, draw the image of quadrilateral R when it is translated by the vector -4, 5. So -4, 5 translation means 4 to the left, means 4 to the left, 4 to the left, that's a -4, and 5 units up, 5 units up. That's what that -4, 5 means. All right, so just move the quadrilateral by these units. I just need to move, because a translation, you just need to move 1 point and then draw by the same shape around that 1 point. All right, so let's look at it. And it's quadrilateral R that we are moving. I want to call it T, the image T. So it's R that we're moving, this one. So 4 to the left and 5 up. So let's say we're doing it with this point. I want to see where this point goes. And then draw by the same shape around that point. Okay, maybe use this point. 4 to the left, 5 up. So 1, 2, 3, 4 to the left. So it's coming here first, then 5 up. 1, 2, 3, 4, 5. But this point is coming to right here. 4 to the left, 5 up. And then once you get that, you'll draw about the same shape around that 1 point. 4 to the left, 5 up. It makes sense, because if you're at coordinate, if your coordinate is at 4 and go 4 to the left, you're going to reach an x coordinate of 0. If your y value is at 1 and go 5 up, you're going to reach 6. So that's correct. And just draw about the same shape now around that point. So we're going to draw this side first, which is 3 units. 3 units. 1, 2, 3. Then this side up here, which is 1 unit up. 1 unit up. Then this side, which is 3 units up as well. 3 units up to here. And this diagonal piece completes the shape. Complete the shape. And it's supposed to label it T. That is it. What we got at that? Are you okay? All right. No answer. And take silent means consent. Let's assume. All right. Yeah, nobody answer none. No, they have to learn. So I say, if I'm not right, and nobody answer. I say, not right. Because I expect if you're not all right, to say something. Because you're here to learn. Anyway, next question says, on the grid, draw the quadrilateral R, draw the image of quadrilateral R after it is rotated. See it now, 180 degrees about the origin. So this one, no, you don't want to have to construct this one. You don't want to have to construct this one. Right? It's better for you to know that a 180-degree rotation about a point is the same as reflecting through the point. Same as reflecting through the point. And also, you can actually calculate the coordinates. Calculate the coordinates and see what would happen to the coordinate. Let me show you. So, a 180-degree rotation about the origin, the matrix is -1, 0, 0, -1. That's the matrix for reflecting to the origin, and which is same as a 180-degree rotation about the origin. If you take this matrix and see what happens to a general point, let me show you. What happens to a general point? Call a general point XY, for example, and work it out and see what's going to happen. The -1 times x is going to become a -x. And the 0 times x is 0, And minus 1 times y is going to become a negative y. What that means? It means that the x point xy is going to minus x minus y. So you take all the coordinates and just negate them, and you'll have your image points. Simple as that. Take the coordinates on the object and just negate them, and that is your image point. So that's how you can actually know. So one important thing is to know the matrix for the transformation that you want. And then you use the matrix to work out what happens to a general point. We'll call it a general point. Call it xy, and the calculation shows you what will happen to all the points. Like anything that happens to one point under a transformation, same thing happens to all the points. And all that this transformation does is negate the coordinates. So a point 3, 4, for example, it's going to go to minus 3, minus 4. I can do the transformation that way, easier, rather than try to actually construct the rotation. Calculate it out. All right? So let's do it. So we're doing this transformation. So let's do it 1 point at a time. This point is 1, 1. It's going to reflect through here to minus 1, minus 1. It's coming to here, minus 1, minus 1. This point is 4, 1. It's going to go to minus 4, minus 1. 4, 1 is going to minus 4, minus 1. It's going to reflect through here to here, so. That's what's going to go. Reflect through the origin to here. Remember I said a 180 degree rotation about the origin is the same as just reflecting through the origin. But all you know is that this point 4, 1 is going to go to minus 4, minus 1, which is right here. So this point is coming down to here. Easier. Then this point, which is 1, 2, is going to go to minus 1, minus 2. Minus 1, minus 2 is here. So this point is coming down to here. Then this point is what? This point is 4, 4. It's going to go to minus 4, minus 4. Minus 4, minus 4. Minus 4, minus 4. This point, which is 4, 4, is going down to minus 4, minus 4 right here. Those are the 4 points. Just draw the shape around those 4 points now, like this. And that's the image of your 180 degrees rotation about the origin. Simple as that. Right? More things you know, the better. So if I show the construction for it, purple, you're rotating about this origin, this point, rotate it through to here. The same as I rotated around to there. This point, rotate it through to here. Rotate it around to here. Reflection to a point, same as rotating through the point. Rotating. A rotation about a point. 180 degree rotation about a point, same as reflecting to the point. This point, rotate it down to here. Rotate it, same as reflecting to the point. This point up here came down to here. 180 degree rotation, same as just reflecting through the point. But also, we could use the information of the matrix that does it and see what the matrix does. Takes a point, carries it to a point where it negates the coordinates, and just do that with all the points. What I got to that? All right, good. And that is it. I'm supposed to label it M. So this thing down here says M. This is a nice question. I like this one. That is M. All right? That was a nice one. All right, let's go. So we did that transformation. Next topic we're looking for is quadratics functions. These are functions. Functions. They give us those two simple functions, f and g. And I want g of -6. So -6 in the g function there. So it becomes equal to 3 times -6 plus 2. 3 times -6 is -18 plus 2. -18 plus 2 is -16. That is the answer for that one. All right, next question. G to the -1. I want g to the -1. Start with g. G equals what? G is 3x plus 2, easy. 3x plus 2. Inverse it before you transpose. Inverse it first. The g becomes x, and x becomes g to the -1 plus 2. That form the inverse function. This is the original function. This is now the inverse. We just need to get the g to the -1 as the subject on the inverse. Here over the 2 first, it becomes x minus 2, and then divide the 3 under. So you get x minus 2, and this 3 divides under here. That leaves with g to the minus 1. That is it. I.e., that is g to the minus 1 is x minus 2 over 3, and sticking back the of x now. G to the minus 1 of x. That is it. All right? Nice and easy. Next one. They want us to do the f of g and show that it is equal to that. So we want to factorize it. We want to do the f of g. Let's set it up. Remember, f of g, youngster, talk the same thing all day. F of g means g into f. Remember, g into f. Let's write them out. F and the g. So the f is x squared minus 1, and the g is 3x plus 2. 3x plus 2. These are the two functions. Let's write in them out so I can show you how we construct it, how we set it up, right? So the g into the f. It means that we're going to take all of this g. We're going to bring all of the g and put it into the f where the x is right here. That's how we put the g into the f. All right? That's how we put the g into the f. So already know. So the f of g of x becomes that construct that we just draw there. So the x is going to put the 3x plus 2, and you're going to square it. So many times we come with this perfect square that have to expand, and so much time we come with it. I'm going to subtract 1 beside it. Subtract by this one. But I say that. We have to expand this note in order to get that. Expand and factorize in order to get this. All right? So let's expand this first. Perfect square. So it becomes equal to first term squared is 9x squared. Then twice the product of the 2. So you multiply these two things, you're going to get 6x, and then double it to 12x. Second term squared is 4. And then subtract this 3. Subtract this 1, sorry. Thinking about the answer. Subtract this 1. And this becomes 9x squared plus 12x plus 3. And I say the factorize the 3 first. So let's factorize the 3 out of these two terms. So we're going to factorize the 3 out of it. We're going to get 3 into 3x squared plus 4x plus 1. But understand that? But understand that? Factorize the 3 here. And then this now is going to factorize into these two factors. Let's write it, right? So it's going to become that. So this now is going to become 3 bracket, 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 bracket. All the factors of 3x squared is 3x and x. All the factors of 1 is 1 and 1. Signs are the same. They are both positive. Everything positive. So it's the same thing that I tell us to show. So we have done it. Shown, I can say, quite easily brushed aside. Yes. Next part is hence solve this now. Hence solve that equals 0. So remember, this was equal to 0, right? We're putting this equals 0 now. But the f of g is this, and you're putting it equals 0. So to solve this is to put this equals 0. So you're going to have now 3 into 3x plus x plus 1 times x plus 1 equals 0. We divide by that 3 gone. So the product of this equals 0 that is left. Because the 3 is not equal to 0. So it's 3x plus 1 times x plus 1. That's now equal to 0. So already know. If this factor equal to 0, I'm going to take the negative 1 and carry it over, become a negative 1, and then divide under the 3. So you will get x equal negative 1 over 3 as one answer. If this bracket equal to 0, you take the negative, take the 1 and carry it over, becomes a negative 1. So the other value is x equal negative 1. So that or that. Those are the two values of x. Very good. X equal negative a third, or x equal negative 1. Done. Nice and easy. I can do one more question after this. More maths equals better maths every time. Want the exam to be soft, you have to put in the hard work. Stop playing so much games. 1 o'clock, don't know and play a game they want to play. You play too much game. Can give my company exam paper. Eh? Too much games, man. Too much games. Here's a function. You give it a graph. It's always nice when they give it a graph because you can get everything you want off the graph. You can get the XT and your YT and all the things and your y-axis intercept. And your turning point right here to XT, YT. And your axis of symmetry is right at the middle there. So everything is on the graph. All right. So that is the function for this graph. And I draw the graph for you. It's easy to draw it for you already. And it says, from your graph, state the roots of the function. The roots are the x value of the graph intersect the x-axis. What are you talking about? The roots are the x value where intersect the x-axis. So these are the roots. See them here? Roots. These are the roots. This is one root. This is the other root. And the root are the x values there. So it's x equals 1 over this side. X equals 1 over this side. And this other one is x equals -2. X equals -2. Those are the roots. Where the graph intersects the x value, x-axis. That's what I mean. I don't like the wording of it, but that's what it is. So it's x equals -2, x equals 1. Those are the roots. Are they good? Next one. The coordinates of the y-axis intercepts. The coordinates, the plural word. It means I have to give both coordinates. Y-axis intercept coordinate is 0, C. So it's going to be 0, -2. I already saw that the C was -2. See there? We can also see the point here. This is the y-axis intercept right here. Is a y-intercept. 0, -2. Because it's coordinates, you have to put this value there first. You cannot just write -2. You put -2 alone, that's only the y-axis, that's only the y coordinate. The sense of coordinates, plural, so we give them both. This is how you write coordinates. With the 2 values in the bracket, that's how you write coordinates. So you cannot just put -2. -2 is only the y coordinate. The sense of coordinates. So we give both of them. This. If you don't get that, you're not getting the mark. All right? Everything important. Next part says the minimum value of the function. So YT value, the one. The minimum value. The minimum value is the YT value. The Y value, the turning point. The lowest Y value on the graph. The lowest Y value on the graph went down to. That's a YT value. So you're gonna write that. So YT value. What is it? Lowest Y value is where? You have to estimate it. What's the lowest Y value right here? So this, what is this? You have to kind of estimate it. Now watch this now. So this is a -2. It's a -4. So this is 2 intervals, and there are 1, 2, 3, 4, 5 lines, 5 spaces between. That is it's two units. This is 2 units wide, and there are 5 lines here. So each of those little boxes, or each little small space is 2 divided by 5. 2 divided by 5 is 0.4. That's all. Because it's 4/10. Right? 2 divided by 5, that's 0.4. Let's check it and make sure we're right. So it should be -2.4. It should be -2.8. It depends on. Let's double check it and make it sure. It depends. So we say there are 5 intervals there, but the unit is 2 units. They want to know what each of these little things is, right? Each of these little intervals, what it is. And to do it, we can say it is 2 is a space divided into 5 little lines. Right? 2 is the jump divided by 5 little lines. So each line we get in 0.4. 2 divided by 5 is 0.4, right? But it's 4/10. So that's -2.4, 2.8, 3.2, 3.6, and then 4. See that? So we are correct. See that? So right here, so then, you notice right here, the minimum point is right on this, so right on the negative 2.4. See it come down to it on this line right so? That's negative 2.4. Everything important. We'll put 2.25 in it. 2.25 is wrong. So negative 2.4 is on that. But good? Negative 2.4. So this is negative 2.4, the lowest Y value. Negative 2.4. Lowest Y value. The equation of axis of symmetry is x equals the xt value. Axis of symmetry, x equals xt value. We need to know what that xt value is. It's the x value at the turning point. Let's work it out. Let's look at it. The xt value where that turning point is. Let's look at it right here. Okay, but this is the minimum point. You know? So the axis of symmetry will be the line right on the middle here. So look horizontal and scale different. So this is 5 lines to 1 now. So each of these little lines is now 0.2, right? Or you can say it's halfway between 0 and negative 1. So that's negative 0.5. What about agree with that? Halfway between 0 and negative 1. Halfway between 0 and negative 1 is negative 0.5. Right? So actually this point, this point, which is the minimum point, xt, yt, will be the point, negative 0.5, negative 2.4. That's what that point is. So this is the xt value. So the axis of symmetry, that blue line up the middle here, so now. This axis of symmetry line up here, so now. That line. See there? That divides the graph half and half, equal distance from it. Is the line x equal negative 0.5. X equal the xt value. That's the line of symmetry. X equals negative 0.5. And they wanted the minimum point. Never asked for it, you know, we have to want the coordinates of the minimum point. The minimum point would be xt, yt, which would be negative 0.5, negative 2.4. That would be a minimum point. If they wanted the minimum point, if we look at the difference, that's for the minimum value. It's a y value. It's a y value at the turning point. That for the value of x, for which the function is minimum, is the same xt value. It's the x value at that minimum point. That for the minimum point, you have to give them this. So minimum value different from minimum point. Minimum point is a point with coordinates like this one. Minimum value to lose y value on the graph. It's the yt value. Axis of symmetry is always x equals the xt value. Whatever the xt value is, but it is the vertical line passing through that minimum point. So the vertical line has the same x value, equation has the same x value as the point that it passes through, as the x value point that it passes through. X equals 0.5. So this axis of symmetry line is x equal negative 0.5. X equal negative 0.5. That equation of that vertical axis of symmetry. I like this question a lot. Next one says, on the same axis, draw the line y equals 2x plus 4. This line is drawn, pass through the y-axis at 4, y-axis intercept is 4, and the gradient is 2. Remember, you can use the gradient rather than run from point to point. Or you can find 2 points on it and draw the straight line through them. All right? So y equals 2x minus 4. We know it pass through 2x plus 4. Pass through 4 on the y-axis. Let's go and do it in per. Let's draw that line in per. So you pass through 4 up here on the y-axis. We know that already. Pass through here. All right? And it is y equals 2x plus 4. So watch this now. Gradient is 2. So it means a rise over run equals 2 over 1. A gradient is 2. 2 is same as 2 over 1. So run, so from this point to get to other points, we can rise 2, run 1. Rise 2, run 1 to get to other points. And from this known point, to get to other points, we can use the gradient and rise 2, run 1 to find other points. Remember, gradient can be used to do that, right? So remember now, from 4 to 6 is the rise of 2, and then the unit across here is 1. So when you run 1, you're going to end up here. Rise 2, run 1, you're going to end up here. Rise 2, run 1, you're going to end up here. Rise 2, run 1, you're going to end up here. Rise 2, run 1, you're going to end up here. So you see all those points on the graph. I'm not rising 2 grids. I'm rising 2 units. The y-axis have a different scale than the x-axis. So this is 2 units. From 4 to 6 is 2 units. Run 1. 1 unit is 1 grid horizontally. Or 2 units is 1 grid vertically. But understand that. I'm not rising 2 grids, run 1 grid. I'm rising 2 units, run 1 unit. So the scales are different on the y-axis and the x-axis. So be careful. That's a 2 units rise from 4 to 6. That's a 1 unit run from 0 to 1. Just that on the y-axis, each grid is 2 units. Vertically, horizontally, each grid is 1 unit. You understand that? Good. And then you can also go the opposite direction to consider the line. So, see this rise 2, run 1, it can be -2, -1. So rise -2, run -1, still equal 2. So we can go the other way. So watch this now. Rise -2 means that we'll come down 2 and go back 1 to here. Come down 2. That's rise -2. Go back 1 to here. So you see, these 2 points are the important points now. We intersect the curve. Here and here are the 2 points where our line is going to intersect the curve. Because I must ask you that. Because I must ask you something about the points of intersection. Those 2 points are the 2 critical points right now. If we continue, rise -2, run -1 to here. So all those points are on the line that I want. All right, so we're going to use that to draw a straight line through those points, and it's the line that I want me to draw. See here, so that is it. That's the line. So this is the line now that we just wanted. That line. And I must ask for these 2 points. And you can see they intersect at the point. Which point is that? This point is 310, intersect at 310. And I also intersect at -20. -20. The line and the curve intersect at 310, -20. So let's see what they're going to ask us for. They must ask for something about those points of intersection. They don't ask you to draw the line just to draw it, see it. They must ask you something now relating to the points of intersection. Let's see what they ask. So it says no. Using the graph, determine the solution for the pair of simultaneous equation. The solution for the pair of simultaneous equation is the points of intersection. That's what when you solve equations simultaneously, that's what you're doing. You find the points of intersection. Or saw it on the graph. It's -20 and 310. -20 and 310. See them there? Where they intersect. Right here says 310, right here says -20. So you don't have to work it out. The graph tells you where they intersect. Very good? Nice and easy. Like this question a lot. Love it. Love it. All right. Another question here? What time is it? Okay, one more question. No more secret, better maths. Don't believe it. We have 15 minutes left. We have 15 minutes left. And I talk to your father about you. You know, I can grade one in a fourth form, man. Me I watch, you know. You underperform, brother. You underperform, brother. You make your brother outshine you. Eh? You make your brother, you make your brother outshine you, man. Eh? 20, that's January 20, June 20. We can do one more paper. June 2020. We can see if we can find January 2025 in the device here. So, well, it's supposed to be in here somewhere. January 2025. I don't have it, you know. I must have it. Somewhere inside here. Let's see. Must have it. January 2025. I have it. Have it in a movie, not in the device. Hold on. Must have it somewhere. Hold on. Hold on. Must have it. Must have it somewhere over here. So. Must have it somewhere over here. I must have it somewhere here. There you go. Yes, I must have it. See if this is it. Oh, I get this far. It's not it. Paper one. Let's go again. January 2025. There you go. Must have it. In here, Mr. Shaq. Must have it. And another one. So I have some right upon it. Let's see. Let's see, let's see, let's see, let's see, let's see, let's see, let's see. See. January 2025. Last year, January. Da, 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 da. Transformation. What? No, oh, no transformation I was last year, January for 3. I think I remember that, you know. I said, oh, I set a transformation. All right, let's do this function here. Yeah. Let's do this function. Let's do this functions question. Let's do this functions question. All right, let's do this functions question. So I don't see no quadratics and I don't see no form. I don't see no transformation. That's hardly about me, no. See transform. And see, we don't do no calculation transformation yet. No why, but we've been looking at the last question. Yeah. Better run that. Okay. And the transformation. Hey, we'll do some more next week. And we'll do some of them calculation transformation. The matrices. We don't know matrices transformation. No. Hey, we're doing it all day next week, Saturday and Sunday. All day Saturday, all day Sunday. Mathematics all day Saturday. Mathematics all day Sunday, right here. 9 a.m. to 9 p.m. Now we are doing all day. The last exam before, the last paper, you're not supposed to say nothing. You're supposed to, hey, I'm supposed to happen for that for a teacher like me, you know. But we need to go in them with our work there, you know. Of course. Multiple choice at 30% of the exam, and you think multiple choice at 1% around 30% of the final grade, you know. That's a lot. That's a lot. 30% is a lot. Because if you get, what you must do is get all 30% on the multiple choice. and get all 20% on the SB, and you're at 50% already. And then you just juggle upon the paper 2. You juggle upon the paper 2. So we can't take the multiple choice for granted. We have to go hard for the multiple choice. I tell you something. I tell you what. I tell you what's gonna happen. After you do the paper 2, you're gonna see that. No, you're gonna see that you need the paper 1. Promise you. I'm telling you. Yeah, we shall see. Anyway, let's go. F and G, when we test and see which one do better on. Paper 2 or paper 1. That's a true test. Give you a paper 2 and give you a paper 1. Give you a paper 2 and give you a paper 1 and see which one do better on. Anyway, we need the paper 1. It's 30% of the marks. We can't take it for granted. A lot of people take paper 1 for granted and it costs them. It's 30% of the final grade. So we need to get all the full 30%. So after the paper 2 done, we'll go hard at the paper 1. Like crazy. We're going to multiply choice all day, every day. Anyway, let's go. F of x and g of x. F of x and g of x. They want f of minus 2. So we're going to put minus 2 in the f function right up here. So it becomes equal to 1 plus, so we're talking please, 3 times minus 2 divided by minus 2. This is minus 2 right here, so. And then minus 1 beside it. Minus 1 beside it. Careful with those negatives now. This is a negative 6. So 1 minus 6 is negative 5. It's become 1 minus 6 with a negative 5 on the numerator divided by negative 3 on the denominator. Negatives cancel, I end up getting 5 over 3 is the answer. 5 over 3 is the answer. Negatives cancel. Next one, the one f of g. F of g means g into f. G into f. G into f. G into f. That means taking all of the g, I'm going to put the g in the f right here where the x is, and also right here where its x is. That's where I put the f, the g into the f. So setting up that construct. So be talking, please. So f of g of x. You can go outside or take a phone call, please. Becomes 1 plus 3 times where the x is, we put in 5 minus x divided by divided by 5 minus x, and there are minus 1 beside it. Minus 1 beside it. And then simplify that, right? So this becomes 1 plus, expand this bracket now, we're going to get 15 minus 3x divided by, this is the minus x by itself, a 5 and a minus 1 becomes a 4. 5 minus 1 is 4. This reduces to 16 minus 3x. 16 minus 3x over minus x plus 4. Leave it like that. That is it. All right. So I turn this around and put 4 minus x. That's fine as well. But that is that. So we can get this off. It's not coming off. It's stuck on it. So this question says derive an expression in terms of x for the inverse of f. That's what this one. F to the minus 1. I don't know where this comes from on it. F to the minus 1. It's my time in that, you know. F to the minus 1. So I want f to the minus 1 now. So you see the inverse of this composite, this rational function up here. So it's f equals, what is it again? 1 plus 3x over x minus 1. 1 plus 3x over x minus 1. 1 plus 3x over x minus 1. I want us to inverse that. The rational again, careful, right? Follow the step. You see small amount of space that I give you. So when you do that, you can divide the space, work half and half, right? Let's go. So when I inverse this first, and the f becomes x equals 1 plus 3 times this x becomes f to the minus 1. And this x also becomes f to the minus 1. Minus 1. Then take this denominator and multiply it across here by the x. Kind of expand it out into separate terms. So you can group the like terms on one side. So when you take this and multiply it across here, it's going to be x times this first, which is x times f to the minus 1, and then x times this negative 1 is negative x equal, this on the right side stays as it is, 1 plus 3 times f to the minus 1. I take this 3 f to the minus 1 and bring it over this side, take this minus 1 and bring it over here, transposing. I want to get everything with f to the minus 1 on the same side. So it's x f to the minus 1. When this comes over, it becomes a minus, a negative 3 times f to the minus 1 equal. This one stays on the right side. This x goes over there and becomes a positive x plus x. Let's continue up here. Let's continue this up here. So then now I'm going to factorize the f out of these two terms. Factorize it. So I factorize the f to the minus 1. I'm going to get an x and a minus 3 in the bracket. X minus 3 in the bracket equals 1 plus x, same way. 1 plus x. I take this x minus 3 and I divide it under here now. So I end up with f to the minus 1 equals 1 plus x over the x minus 3. And that is your f to the minus 1. That is it, the inverse. But good? Nice practice. Nice practice. That done. Times it now. Hey, now run it woman now. Let's see the last question of that transformation right now. Lazy like what? Lazy. All right, guys. All right. That is it. I'm going to share the video in the group. And on the channel, you can go back and watch anything you want to watch. If you need to see again, you can go and watch it. And that's it, everybody. See you next week. I'll do it again. Mathematics all day next week. Mathematics all day next week. All right, bye. Bye, everybody.